That was Tony, right? Yeah. I'm meeting him right now.
Hey, Tony, can you hear me? Oh, another Tony. Well, in-person Tony can hear us. Remote Tony, can you hear us? Or hear me at least?
Yes, remote Tony can hear you as well.
Fantastic. We are a little past 1, but we're just going to give folks maybe a minute or 2 to stroll in here, and we'll get going in just a couple minutes.
Sounds good.
We've hit 105. We've got a few folks here, so I think we'll get rolling. Thanks everybody for stopping in. This is our presentation on storage tank air compliance beyond the basics. We'll kind of cover what our course will include here in a moment, but first, let me tell you about. Let me tell you about who's presenting today, which is myself. My name is Al Reich. I'm a chemical engineer with Barr Engineering Company. I'm out of our Duluth, Minnesota office. And for the past almost 10 years, I've been working on storage tank permitting and compliance efforts in the air quality world. Midstream terminals, refineries, bulk gasoline terminals. Wherever there's a tank, I've been involved with supporting permitting or some sort of compliance topics or activities. To that point, I'll turn it over to Tony, let him introduce himself quickly here.
Hey everybody, I've got a really similar story to Al, except I've been at it a few more years than he has. So looking forward to talking to you about tanks this afternoon.
Great. So enough about us. Since we've got a smaller group, I think it would be great if we could just do a quick around the horn of What type of facilities do you work at? What type of experience do you have with tanks and air quality? Are you responsible for emission calculations? Do you have any specific items you're particularly curious in, just so we can kind of keep the boat pointed in a useful direction for everyone? Maybe we can work from this direction over. Okay. Sure. Okay, awesome. Okay. All right, me too. Gary? Right, in the back? Okay. Kale says hi. Um, okay. And you, sir, in the almost front row. Quick intro, what are you involved in air quality efforts with storage tanks, emission calculations, anything in general? Sounds good. All right, we'll try to keep that general field in mind here as we go through our topics. And kind of how we'll break it down today. We'll start with a review of the air regulatory programs, the general basis for a lot of what we do, right from the compliance demonstration perspective, work into storage tank design, deck fitting requirements as a general overview, and also with considerations to regulatory compliance, talk about air emission pathways and calculations, go over sort of a broad air permitting and compliance topics, current events and other items. And then we have Barr has developed a tank calculation tool to replace or supersede EPA's Tanks 409 program. So we have a quick overview and demo of that at the end here. So without further ado, we will get rolling, and Tony will take it away on air quality regulations for storage tanks. Tony?
And I apologize, I wasn't able to hear anybody when we went through the questions there. So in light of that, if you have any questions as I'm going through this, feel free to interrupt me and we'll take them as we go. So the first thing I wanted to start out with is something very basic, or at least seemingly, which is what a tank is versus a vessel, and different regulations use different terminology. So right off the bat, it's important to understand whether your storage tank or vessel is subject to the particular regulation that you're looking at. So it's important to read the definitions. It's also important to understand potential exemptions, such as a pressure tank or a process tank, or if you're in the oil and gas, whether you're before custody transfer, and then of course your typical volume and vapor pressure thresholds. And frac tanks, I think we actually have a slide on that later that's going to talk about that in a little more detail, but that's a topic that often comes up, whether it's for waste storage, tank bottoms, or whatever else it might be for. Those frequently are used on a temporary basis or even sometimes longer term and need to be considered for regulatory and permitting purposes. So this diagram kind of attempts to show the different realms of storage, where storage tanks are found. You could add oil and gas on here as well, but it'd probably make this even more convoluted. But there's a lot of overlapping things. I think one takeaway from here is the NFSS rules, particularly K, KA, and KB, universally apply or potentially universally applied regardless of what industry you're in. So that's going to be our focus, is on when we're going through the regulations here. We're going to be talking a lot about KB, and the main thing to note is that some of these tangential or similar regulations are very similar or with some slight differences, or they might refer to KB. So just something to keep in mind there. And Al, feel free to add anything as I'm going through as well.
You got it. Tony.
Ready for the next slide. So as I said, this goes into a little bit more detail about the common air regulations. So K, KA, and most importantly KB for volatile organic liquid storage is one of the most common ones that we all have to deal with. There's also requirements under NFSS UU for asphalt processing and roofing manufacturers. QQQ for petroleum refinery wastewater streams, Quad O and Quad OA for oil and gas. And then under Part 61 niche apps, there's a couple subparts that potentially apply there. Subpart Y for benzene emissions from storage vessels, and benzene waste operations niche app for those of you in either chemical plants or refineries. Again, I didn't hear the background, so I don't know if we've got anybody there with that work in those areas. Then we get over to the Part 63 niche apps, also known as the MAC standards, and there's a whole host of them there that have storage tank requirements associated with them. Again, some of these will point to another regulation, but overall they're pretty similar requirements. I'm not going to read through each of these. We could just hop to the next slide. Then on top of that, there's state regulations, and we just have tried to give a couple examples. This obviously is not an exhaustive list, but Illinois, for example, has Part 215 that applies to loading operations and storage operations. There's a separate Part 218 that applies specifically to the Chicago area. There's some other examples here. So the main point is, don't forget about your state regulations. So the structure of air regulations follows somewhat of a common pattern where there's the applicability definitions and exemptions, which we talked about a little bit already, and it's important to go through those. Sometimes it's pretty obvious what you're subject to, but other times it's not, and it takes a more detailed look at the requirements. And then there's your actual standards, which might involve work practices, such as inspections, or if you have a fixed roof tank, it could be an actual emission limitation. Typically for floating roofs, those standards are work practices and not actually numerical emission limits. Testing may be required. Inspections, again, might fall under that testing category. Monitoring of your operations to ensure that you're meeting any required standards, and of course record keeping. If you don't have records, then you basically didn't do it, and in some cases reporting is required. So most regulations have some element of each of those topics. Starting out basic here, we'll get into some of the details. So KB applies to storage tanks that are constructed, modified, or reconstructed after July 23rd, 1984. and that have capacities greater than roughly 20,000 gallons. Some notable exemptions include tanks that are between 75 and 150 cubic meters that have a maximum true vapor pressure less than 2.18 psi, and tanks greater than 151 cubic meters with a vapor pressure less than 3.5 kPa, which would be about, what is that, 0.2 or something like that, or 0.5 psi, somewhere around there, really low. So if you have low vapor pressure material, it won't trigger KB applicability. Pressure vessels that are designed to operate under pressure and don't have routine emissions to the atmosphere are exempt. Mobile tanks are exempt as well. And there's a couple others in there, but there's a few for discussion purposes. Next slide. So typically under KB and other rules, if you have a maximum true vapor pressure of greater than 11.1, that's going to require use of a closed vent system and controls. So that's usually the limit we're looking at for being able to store volatile organic liquids in a floating roof tank versus something that needs to be connected to a closed vent system and emission controls. As far as I know, I haven't seen a floating roof tank successfully connected to a closed vent system and control system. I don't know if anybody in the room has experience with that kind of configuration, but there's some technical feasibility issues with that typically preclude that combination from being used.
There was a note that there might be one in Louisiana somewhere, but I think it generally seems to be uncommon.
Yep.
Oh, sure. Gary is noting that it may have come up through a layer evaluation, which would make sense that it's typically uncommon.
Yep. Yep, that makes sense. So just briefly, MacDSS, which is referenced if you do have a closed vent system and controls. KB refers to MacDSS, which requires you to submit a design plan, requires testing of the control device, includes some operating standards for your closed vent system and your equipment. And then again, like all rules, there's notifications, record keeping, and reporting. So I don't think we're going to go into a ton of detail on this one, but just wanted to mention that. So outside of actual regulations, there may be requirements for your storage tanks, such as from air permits. So if you don't actually have a permit document, it might be like in Texas and some other states, a permit by rule or a general permit, where the permitting and rule are kind of combined into one thing. Another source of tank requirements can be the Storage Tank Emission Reduction Partnership Program, also known as STRP, which was a voluntary agreement, I believe, back in the early 2000s for operators with the EPA to reduce air emissions from primarily from slotted guide poles. And they incorporated requirements there that are very similar from MacWW. So basically what the STRP requires is no visible gaps on your slotted guide pole and provides some very specific options for what controls you can use to meet this emission reduction program. I'll pause there. Any questions or comments up till now?
Mm-hmm. Yeah, so Brooks had a question about the STRP being a voluntary program, but then also a source of requirements for potential air requirements for tanks. And I think the voluntary in that, I believe, Tony, correct me if I'm wrong, you could sign on board with that when it initially was promulgated or came out as an early sort of self-disclosure method to address the issue, as opposed to do nothing or potentially face enforcement once the visible gap issue had become identified and communicated for floating roof storage tanks. Anything else on the STRP, Tony?
No, that's correct. You ready to move into inspections?
Oh, sorry. Yeah, you can't see anything. We are good on the questions here. Sorry about that.
Yeah. No worries. So we'll go through a couple of the specific inspections. Again, this is primarily from the NFSS KB lens, which one, this is for internal floating roofs, requires an annual visual inspection from the gaugers platforms. So, and it's to the extent that you can observe. So you're up on the platform, you're looking through the roof, you're probably aren't allowed to break the plane due to safety regulations. So you're seeing what you can. Maybe use a mirror to shine some light in there, or an intrinsically safe flashlight, high intensity, to get a little better look. Some floating roof, or some of the fixed roofs on IFRTs have translucent panels to facilitate those inspections. But not to go too far down that rabbit hole, the things you're looking for are whether you have product accumulated on top of the floating roof, which would obviously indicate a problem. If there's any covers, lids, or seals that aren't closed, or you see holes, tears, detachments, or other openings in the seal, the primary or secondary seal, or the seal fabric. So if you do identify one of these, you have to report that failed inspection within 30 days and either repair or remove from service within 45. I believe you're allowed one 30-day extension under KB.
Sure, Gary is noting that if you have an additional on the fixed roof, access hatches or manways, those are other abilities you can open to get additional light in the fixed roof floating roof tank space. Or do that, yeah, not just from the gaugers platform, but also doing the inspection from those if it helps.
Absolutely, and it may seem obvious if you've got some tank experience, but we're looking for things on the floating roof. But I've gotten the question more than once over the years of this, hatch on the fixed roof doesn't have a gasket on it. Is that a problem? And the answer is no, because the purpose of the fixed roof is basically, from an emissions perspective, it prevents the wind from driving additional emissions and then protects the floating roof from the weather. So it's not intended to be vapor tight, but that question arises. This is another one that this complete out of service inspection, where you might have some misunderstanding between, and I think we'll go into that in a little bit more detail later, but maintenance might think they're doing the inspection in accordance with API 653 and that they're covering everything they need to for this complete out of service inspection, but more often, or almost always, it doesn't check all the boxes. So it typically is its own independent inspection. Under KB, the rule says it must be conducted out of service, but there recently was some language there that allows you to request an alternative monitoring procedure. Actually, I think it's written into the rule now. I don't know if you actually have to request it, Al.
Yeah, so this slide is a precursor to the upcoming more detailed NSPS alternative compliance option. Historically, to request the AMP, and for a while there, the EPA was granting them, and then they kind of pumped the brakes on it. But recently, early this year, the EPA published the final update to AP 42 or to NSPS KB that has provisions to accept MacWW as an alternative compliance option, and we'll touch on that in a little more detail as well.
So some common failures that are associated with these inspections are basically your deck fittings do not meet the design criteria. For example, you may not have a sleeve on your guide pole, or your wipers or gaskets are deteriorated, or they're shifted such that there's a gap between the wiper and the deck fitting that it's intended to control. And the main thing here is just making corrections and documenting those corrections prior to refilling your vessel, and there aren't any reporting requirements associated with these. So EFRs require, in addition, the complete out of service inspection isn't required on a certain frequency, but anytime you do empty the tank, it's got to be inspected prior to refill. And there's also seal gap inspections, as most of you probably are aware. And so there's some common questions or failures that come up during these. Is the seal tight at all tank levels? Do you need to remeasure gap failures following repair at the same tank level as the initial failure? You don't want to skirt the rule by saying, we measured it at 10 feet and there were gaps, and then we filled it up to 20 and there weren't any. So it really needs to be tight at all levels, though the rule doesn't specify that you have to test at a certain level. So it becomes one of those gray areas. Also, common failures include rips, tears, or holes in your seal or the fabric itself. So for these, failed inspections need to be reported within 30 days, and then again, repair or remove from service within 45. Talked about this one already. It's pretty much the same as the IFRT, except that this inspection is required each time the vessel is emptied and degassed, not on a 10-year cycle. You can go to the next slide. So what happens if I change service in a tank to a product that is less than the applicability threshold to require inspections? So for example, you have a floating roof tank that's storing gasoline, but you switch it over to diesel, which wouldn't trigger the vapor pressure threshold for KB applicability. However, if your permit still requires you to do it, like if your permit incorporates the requirements of KB, not just by reference, but the specific language from there, you must still do the inspections as if you were subject to the rule, regardless of the applicability. If you no longer do intend to store gasoline, you may need to do a permit action to remove that KB applicability. Again, it all depends on what kind of permit you have. If it's a temporary event, you could continue the inspections as if you were subject to the rule. And if you don't have a permit and you no longer meet the applicability criteria, you may choose not to complete the inspections. It's kind of a risk-based decision, one of those gray areas, but if there's no underlying permit requirement and you don't meet the applicability criteria, it's probably pretty safe to no longer do those. All right, seems like a good spot for a quick pause. Questions, comments before we get into monitoring and record keeping?
Appears to be nothing on the inspections at this time, Tony.
All right. So some of the basic monitoring requirements in record keeping. One is you need to have a record showing the dimension of the storage vessel and an analysis showing the capacity. routine records of the material stored, the period of storage, and the maximum true vapor pressure during those respective storage periods. And there is a notification requirement under KB within 30 days if your maximum true vapor pressure exceeds the range that you're subject to. So there's a variety of ways that you can determine your vapor pressure from your storage tanks. Do you have a question?
Yeah, I was making sure I wasn't on mute there. There was a note around the exceeding the vapor pressure ranges, and that's in reference to not necessarily the 11.1 PSI threshold, which would be a deviation under most permit situations. However, this is specifically referring to the vapor pressure threshold range for those smaller, unique applicability categories. Yeah, the 0.5 to 3 point or point whatever. Yep. All right, we can carry on here.
Okay. So there's a couple different ways you can look at TVP. One is for crude oils, you can use available data on the RVP and then convert that to a true vapor pressure. So RVP is at 100 degrees Fahrenheit and true vapor pressure is at your actual storage conditions. So using the API nomographs to convert from one to the other. For other liquids, you can use standard reference texts. There's ASTM test methods, noting that it's got to be an appropriate method approved by the administrator or calculated by an approved method. Direct measurement of TVP may be used, particularly for crude oil. It's ASTM D6377, but some states don't have that as an explicitly allowable way to calculate TVP. So before using that, it's important to just make sure that you understand if it's allowed or not. So if your maximum true vapor pressure, I think I touched on this a little bit earlier, if maximum true vapor pressure is greater than 11.1, then you need a closed vent system and control device. So then the couple questions that we've received over the years. So what if your TVP exceeds 11.1 for one day? For example, maybe you received some stock that was warmer than normal, or there was some other extenuating circumstance that resulted in your calculated TVP exceeding that. Our recommendation is that you typically calculate a weighted average based on a weighted average TVP. Keep monitoring, but it's not necessarily a KB deviation unless the monthly average exceeds 11.1. So that's from a KB interpretation perspective, but some state or permit requirements may differ from that. So then what if it exceeds 11.1 for an entire month? So if it's a one-time exceedance, you may not have to install a CVS or a closed vent system and control device, but it could be a Title V operating permit reportable deviation. However, if you expect that to continue, then you probably will need to install that closed vent system and control device.
And one quick note on the calculated weighted average TVP, that is typically a reasonable strategy if you're looking at a tank that stores a variety of products. Everything is kind of pumping in there at the same time and storing and getting stored in there at the same time. If you're receiving segregated individual batches that have that may have a really high TV or high vapor pressure and then a low vapor pressure, and they're not commingling, they're not mixing, there's not actual averaging happening of the material in your tank, the ability to take advantage of a weighted average may not be physically appropriate if that material isn't specifically, because we're looking at the material and then the monthly temperature. So we can average the monthly temperature just fine, but if we're not blending or mixing that material in the tank, there may be some issue with taking a weighted average of that vapor pressure. So it's definitely evaluated on the situation as you handle it. Yeah. Mhm. So you're saying if you're storing, sure. So that would be potentially in the situation of, are you going to run into a TVP exceedance with your monthly temperature at that given time, or are you blending them enough such that you have an accurate, or you can consider them weighted? Sure. Okay. Yeah, so the interesting part about the temperature is from the KB requirements, it says specifically to use monthly temperatures. So to the first point that Tony was making, we don't want to necessarily, if we see that we have a TVP exceedance on a daily temperature spike, it's good to let that sort of raise a red flag and be aware that there could be some upcoming temperature concerns. But that in and of itself would not constitute a specific NSPS KB deviation, but rather the monthly temperature is the definition of max TVP on a monthly average. So the temperature part can be averaged over a month to get that specific value. In terms of the materials stored, it's that commodity or that material at that monthly average temperature. So if your materials aren't specifically being blended or mixed, you'd want to look at it on an individual basis. I don't know, Tony, am I missing something there?
Right, that sounds right to me, because like if you have a high RVP product and you're putting it in a tank, you shouldn't be storing it in that tank, period. If you're not blending. Now, if you had it mixed with another product and it, knocked down the vapor pressure, that's okay. But a high, a pure product or even a high vapor pressure crude oil, you wouldn't want to store on its own in that tank. And sometimes how that's handled is just by, specifying, if you're a terminal, you might have it in your agreements, or if you're a refinery, have a spec that says we can only receive certain products, and here's the limits, here's the cutoffs for what we're able to receive.
All right. We'll press on to notifications and reports.
So if you have an existing tank under KB that, you have a question? Sorry, I was getting some feedback there.
Oh, no, we're good.
Okay, so an existing tank, one that was previously constructed, the main notification reports are whether you have inspection failures that we talked about earlier and your exceedance of maximum true vapor pressure. So when you have a new tank, which is the next slide, there's a slew of different requirements under KB, including construction commencement, 30 days after you start construction. For EFRs, seal gap inspection notification, seal gap inspection report. For IFRs, 30 days prior to fill, prior to your complete inspection, actual startup and certification for both. There's an actual startup and a certification that your control equipment meets the standards that's required 15 days after. And then in some cases, if your permit requires it, you may need to submit notifications of changes to as-built information. And then, of course, there may be some state requirements that you need to consider as well. If you have a modified tank or a reconstructed tank. And just as a reminder, modify it as if you increase emissions on your tank is basically what it comes down to. And then a reconstructed tank is regardless of emissions, did you spend 50% or more of what it would cost to construct a comparable new tank? So if you triggered KB for one of those reasons, there's a reconstruction notification, which is required 30 days after reconstruction commences, a modification notification, which is 60 days or as soon as practicable before the change is commenced. So that's very vague. And then the other applicable inspection and startup notifications for a tank newly subject to the regulation that we talked about in the previous slide. So these would be in addition to those. So what happens if you observe something?
Question here, Tony.
Question. All right.
Sure. So the question was on reconstruction and what to include or exclude into that fixed capital cost for the 50% threshold. And there for tanks, there are, I think, one or two specific EPA issued ADIs, applicability determination index documents, that discuss what should be included as part of that reconstruction cost analysis. The general heuristic for what costs to include are typically costs directly associated with the containerization of the liquid, is the phrase they use. So shell coating would be certainly appropriate. Painting would be necessary. Any steel work. Fire suppression equipment, though, would not be applicable. I don't think you can include the crane costs or other significant external equipment. There's a handful, like I said, a couple of ADIs that do provide a little more context. They don't spell it out perfectly, but they do provide a little more of a defensive base you can use to help include or exclude certain costs. Tony, any other or reconstruction comments?
Yeah, that's a good summary. To expand a little bit more, like site work, dirt work would not be excluded, would not be included, but foundation, like the floor itself of the tank would be. So, and I think one of the things to consider too is if you're including it in the cost of reconstruction, then include it in your cost of a comparable new tank, so that it's in both the numerator and the denominator of that equation. That makes sense.
Thanks, Tony. I think we're good on that one.
Okay.
Real quick before moving on, anybody in the crowd have other thoughts or comments on reconstruction cost analysis or how to include or exclude values? Seem to be nothing else jumping out here, so we'll press on.
So what happens if you observe an issue outside of your normal inspection? So you're looking at a tank and you happen to notice that a hatch is open, but you didn't notice as part of your inspection otherwise required. So is it an issue and how do you handle it? So some things, we don't have a black and white answer for this, because a lot of times, as you know, things are not black and white in air. So, but some things to consider: is there a general duty clause that says reduce emissions and take all reasonable measures to do so? You may want to consider the 45-day repair window and notification as a conservative approach, and just say, even though we didn't identify it as part of our normal inspection, we're going to treat it as a finding and we're going to notify and we're going to fix it. But if it doesn't impact the integrity of the floating roof or any potentially applicable regulations, it may not be an issue. So anybody in the audience have any thoughts on this one?
Or perhaps you have a friend who has a terminal or a tank. Seem to be heads nodding, but no comments at the moment.
Okay. So just a couple notes about some additional tank regulatory programs. We touched on this previously. B1, the benzene waste operation NESHAP under Part 61 may require a closed vent system and control or NFSS KB level controls. MacDSS for petroleum refineries gives you, I believe it gives you the option of WW or NFSS KB, and it specifically outlines what to do in each case. And then MAC 6B, which is the area source MAC for terminals, is again either KB or MAC WW. Am I still going on this one?
Yeah, you will. We'll just do one final check on the regulatory topics that we've covered. Any thoughts, comments, discussion before we kind of shift gears into a little bit more visual storage tank design coverage here? Seeing nothing at the moment, so we can take it away, Tony. I'll pick this up about partway through, so we'll let you get going with the first few here.
Okay. Well, at least now we get away from some text and can start looking at some actual photos, so maybe a little bit more interesting. So the first thing we want to start with is talking about the different types of floating roofs. So steel pan, we've got the diagram on the bottom there, and then a picture of one on the top. And basically it floats by just having that upturned edge. Pontoon style in the middle there, you can see it's actually a closed compartment around the perimeter of the tank. The third style we've got is called an aluminum sandwich panel. Sanborn is one of the manufacturers of these types of roof. It's basically some rigid foam that's covered in aluminum, and then the seams are heat welded. And I've walked on one of them. It didn't make me feel super comfortable, but they're surprisingly sturdy. And the advantage to those ones are they can, like if you're retrofitting an older tank or need to replace a roof, especially on an internal floater, you can install these in pieces and get them through shell manways. So you can build a whole floating roof by putting the pieces individually through the shell manway instead of bringing them over up from the top. Another common one for internal floating roofs is this aluminum skin and pontoon floating roof. So pontoons more in the sense of what you see on a pontoon boat. And so the liquid in this case is not in contact with the bottom of the floating roof, which is a distinction between other floating roof styles. So there's always a vapor space between the liquid and the floating roof, whereas in the other ones we looked at, and you can see in the middle diagram, the middle bottom there's a line. I don't know, Al, if you can point, but there's a line where it shows the liquid level under the seal, and you can see it's above the bottom of the floating roof. So the roof actually, well, the weight of the roof will push that level up, and it's always floating in contact with it. So in that middle one, it's a double deck roof, which is, as it sounds, there's two layers of steel. And the last one, don't have a picture of, but it's kind of like a pan, except it's got open top bulkhead compartments instead of closed top bulkhead compartments that are typical of a pontoon. So all this is important because these are parameters that go into emission calculations and or have regulatory requirements associated with them. So we're going to go through each of the different types of deck fittings. First one we'll start with is an access hatch. This particular one is a rectangular, but they come in various shapes and sizes. The cover, seal, or lid needs to be in the closed position. So this is a summary of those requirements. And then again, this is under KB, and the cover has to be bolted and gasketed. And you can see in the photo there, the gasket between the plate there. And then it has to have a projection into the liquid, which I think we have a slide on that later that shows what I mean. For full contact roofs, that doesn't apply, but for those skin and pontoons, the projection of that well actually has to extend down into the liquid level. So, yep, here's the slide that shows that, where you could see the liquid level is where that first red arrow is pointing. It's somewhere on the pontoon itself. And the deck fitting there, this is a stub drain pipe that projects below where the actual liquid level is. And another example on the bottom right of I think that's a support column, either that or a guide pole, but I think it's a support column. So that well, the liquid level will be up where that red arrow, second red arrow is pointing. Automatic gauge float wells, these aren't typically installed on new tanks, but they're pretty common in older tanks. It's basically, as it sounds, it's a float that helps to gauge the level of the tank. So that cable you see coming out through the top goes up over the top of the shell, down the other side, and comes down to a level indicator, and that lets you know what level that roof is at. So again, like most of these, it's got to be, the cover on there has to be in a closed position except when in use, and it's got to be bolted and gasketed and have a projection into the liquid.
And one fun note here, bolts aren't specified for the EFRT automatic gauge float well under KB. However, in MacWW, a bolted cover is required whether you have an EFRT or an IFRT.
So fixture support columns are used to support the fixed roof on internal floating roof tanks. And so those extend through the floating roof down to the floor, which creates a projection or a penetration through the roof. And so I guess the way to think about all these is anytime you've got a potential path for vapors, that pathway needs to be gasketed, typically under KB. So that's what this is showing here. There's the gasket on the upper right, and on the left one, they don't specify wiper for column wells, but you could kind of see it's a wiper. It basically eliminates that gap that's between the cover and the column itself. So gauge hatches, which are used to take samples or do a bottom survey, for example. Again, same requirement to have that cover, lid, or seal in the closed position with no visible gap, except when you're using it. And that cover needs to be gasketed. So in this case, you can see the gasket on the lid itself and also on that flange that connects the top part to the pipe that goes through the roof. So both of those are gasketed.
One way we've talked about this in trying to help provide context to clients or other folks trying to understand or make sure they've got their tanks appropriately controlled is the no metal to metal contact when you're talking about your deck fitting cover and opening, and that's a pretty good standby to check with. If something isn't gasketed, it probably should be. Even if you're not subject to KB, it's typically not a bad plan to just make sure you've got that in place.
So ladder wells are on fixed roof tanks, and again, require a gasketed cover. And typically there's a wiper or some other piece of rubber there where that arrow is pointing to show that there's no visible gap. Sometimes the one leg of that ladder will also serve as a slotted guide pole. So they make these sleeves specific for ladder wells to meet the control requirements for a slotted guide pole or gauge pole. Again, just some additional photos here of the gasket. Notably under that one lower left one, might argue that there's a bit of a gap between where the gasket comes together in the corner. Oh, shoot.
The projector
I screwed that one up.
isn't super great, so it's a little bit maybe difficult to tell from the back. But as Tony's pointing out, we've mentioned the 1/8 inch gap provisions generally when we're talking about the other inspections, and I'd say that could be one to cause concern.
Sorry to take away somebody's opportunity for the bonus point. Go to the next slide here. Rim vents are used to leave the pressure between the seal and the roof. So again, these are typically I've seen on older tanks. I don't see them specified or installed on newer tanks anymore. It gets a little bit tricky because some of them use like a weighted pallet vacuum and pressure type configuration as shown in the lower right. So it's really hard to tell whether it's gasketed or not. So sometimes you gotta, if you really want to know, you gotta look at vendor drawings or take it off and take it apart while the tank is out of service to verify it meets compliance. So a lot of times they're just cutting these off and welding a patch over them instead of leaving them on anymore. So roof drains, there's a couple different roof drain configurations. And that first photo on the top of it, you'll see a sump, and then that water that goes down in that sump goes through a flexible hose that goes to the shell exterior and discharges into the tank dike. So that's not an emission source. There's no way for the vapors to get through that. The emergency overflow drain is basically just a hole that would go directly into the liquid. So if you get a whole ton of rain and need to drain it quickly, that's the point of the emergency overflow, is you get water into your product, but you don't sink your roof. And sometimes those could be just open, or sometimes, as in the photo on the right, they might be plugged with a threaded, I guess, plug.
That would be the requirement. Yeah, there are some legacy tanks that we still occasionally see an open thing that may exist, but then typically the recommendation is to address that with the slotted membrane, slit fabric I mean, it's clearly some water from that picture there, so they are a little slow on the drainage. Yeah, so it's definitely I think we don't think we have a picture of what Gary was noting, the 90% covered, you know, essentially the slotted fabric closes off the opening enough that once the weight of the water builds up, it'll push it open and allow it to passively drain while still maintaining a reasonable amount of closure to the opening.
So roof legs, the main requirement there is that they have a protection into the liquid. Controls are not required for roof legs under KB or MacWW. There are ways you can control them, like the socks shown on the second picture there. And the left one does show, I guess the one requirement is the projection in the liquid, which for a full contact roof wouldn't need that projection, but you can kind of see what that would look like on the left side. So on the right there is not a leg, but it's a cable supported roof. And so that shows you a visual of what that looks like from both the top on the right side and then the underneath of it on the left side. So whether you account for those as roof legs or not is probably, you know, it's one of those gray areas questions. You could conservatively account for them. There's not much of a pathway for emissions. It looks like there's a little bit of one maybe through where the cable goes through, but even then it's pretty minimal.
And one closing note on roof leg socks or other gaskets or roof leg controls. Typically, all the deck fitting controls we've discussed to this point, if you're taking a tank out of service or constructing a tank and putting it into service for the first time, need to be installed and in place before the tank goes into service. With roof leg socks or other leg-based controls, those can typically be, as long as you don't have other back you into a corner permit conditions, be installed after the roof is floated. You can pin your legs in your low leg setting and then install the socks or the gaskets or the boots to ensure that you've got a reasonable or the most flexible operating control range for your for the purposes of your emission controls.
So this is a sample well. The cone there is to kind of help guide your sample collection container into the hatch there. And as Gary was talking about, you can see this one does have a slip fabric cover on the right side, which is a requirement. So that you might see on roof drains as well. And then similarly, to all most fittings other than vacuum breakers needs to have the projection into the liquid.
For those in the room here, the projector is definitely making the slotted fabric membrane a bit difficult to see, but it's not just a black hole into the underside of the floating roof. There's that slip fabric covering there that would help prevent or close off that emissions pathway.
So for a slotted guide pole, gauge pole, or anti-rotation pole, regardless of what function it serves, it requires a cover, seal, or lid in the closed position, no visible gap, a wiper, either a sleeve or float. The cover needs to be gasketed. It has to have a projection in the liquid. It has to have a cover or cap on the top of the pole, so way up at the gauger's platform. And often that is some kind of automatic gauge, like a radar gauge or something like that. If not, then there just needs to be some other kind of cap. It just can't be open. Another option is having an external flexible fabric sleeve seal on that basically covers the whole outside of the pole all the way up from the deck of the roof all the way up to the gauger's platform.
One of the other STRP requirements or options for slotted poles could also be to put a solid pole down through your slotted pole. However, that effectively negates the benefit of having a slotted pole to prevent buildup and enable mixing and getting better readings and gaugings through that. So there are a couple other options as well, but floats can be challenging, and the external flexible fabric accordion style cover is a little bit newer, but certainly we've seen it used from backed perspective sometimes and just as alternative options as well. Correct. Yep. That's the yep. Correct. Yeah. The Weller opening is okay as long as you've got that full contact. Yep. Or the projection there. Yep.
Just a couple of photos here. Use the term slotted. That can actually mean long, wide slots, like on the left, or it can mean holes, like on the right side. And there's some various pictures there of the wipers and the gaskets. There's all kinds of different designs that you may encounter. And it's just really, the main takeaway is, okay, where's the emission pathway here, and is that gasketed or is that have a wiper? And then on the lower right, you can see that picture of the emission sleeve, which is basically designed to minimize the vapors from being able to travel up through the slots and out the top of the floating roof, through the pole and out the top of the slots that are above the roof. And I think this is just another up close picture of a wiper and a gasket and a slot, which in this case is a hole. One thing that, if you're out inspecting a tank, one thing to keep in mind is that sometimes there might be holes or slots only below the floating roof, but then above the floating roof, there aren't any. So as long as they're not above the floating roof, that typically can be considered a solid gauge pole and not a slotted.
With the note that you should be cautious or conscious of your high and low leg settings to ensure that you don't look good from the inspection perspective, but then on your working bottoms have potential slot issues to deal with. Correct. Yep. Yeah. So to Tony's point, if you've got, for whatever reason, your vendor started drilling holes, or they find that there's some benefit to having a few holes, you can still be a slotted, or I'm sorry, an unslotted pole if you have holes in your pole. But if they can be potentially above your floating roof in operation, that's where we run into problems. Not problems, but it's just a slotted pole.
So unslotted poles are pretty much same requirements, except you don't need the sleeve because there's no holes to cover up there, and you wouldn't need, whether it's an internal sleeve or that external flexible fabric sleeve seal, which are designed to cover those holes or slots. Those aren't needed, but otherwise you do need the wiper, the gasket, projection in the liquid, and the cover cap on the top of the pole. And this is just a picture of one. Shows the gasket there. So stub drains are utilized on internal floating roofs for the purposes of, if you unintentionally get product on the top of your roof, there's several of these drilled throughout the tank. The little ping pong ball will float up and the liquid will go back into the tank instead of being on the floating roof. So the requirements under KB are to have a projection into the liquid. Under MacDWW, it requires you have a 90% cover, which is what is shown there with that little ping pong ball. I think that literally is a ping pong ball.
Yeah, I mean, that's the, it may be marketed with an upcharge as a tank control device, but essentially it's a hollow, buoyant ball type material that will lift up when liquid is there to allow for drainage, but otherwise somewhat seal off the opening.
And I don't know the answer to this, Al, if the new AP 42 allows you to claim controls on your stub drain, but the old version did not. You just, whether you had a cover on it or not, you just counted it as a stub drain, but didn't have the option to specify it was controlled.
You know, that's a good question. And all of the numbers and figures I've got off the top of my head, I don't have that one. But in terms of regulatory compliance, I know, oh my gosh. And I'm in terms of regulatory compliance, however, you know, the stub drain is a generally, you know, I guess IFRTs can have a few or a lot depending on the design. I think they're somewhat less common on more modern tank designs. But in terms of the control feature, that's definitely a standard requirement for the MacWW compliance purposes. And again, an important note to be mindful of if you're looking to take advantage of the alternative compliance option under NFSS KB to take on MacWW as the alternative compliance strategy, you then may have to reckon with some incongruous deck fitting designs.
So vacuum breakers notably do not have the requirement to have a projection into the liquid, because if you did, you could potentially buckle your roof. So the main requirement here is that they be closed at all times, except when your roof is being floated off or landed on its supports, and to have a gasket on the cover. And that can be accomplished a couple different ways. It could be from the cover itself, or it could be on the pipe. You could see both ways of doing that.
I can take over from here, Tony, now that you've got through the visual portion of the presentation here.
Sounds good.
All right, so we've just covered sort of the general overview of floating roof design, deck fitting requirements, and general floating roof parameters. What are we going to do with them? Why are they important? What do we need to do with those? And it's important for a variety of reasons to approach this from a pretty significant data management perspective, because we want to have accurate representations of what our tanks are designed as, how they're built or constructed, and what's on them, not just from the emission calculation perspective that we'll get into in a little bit, but also more directly from the regulatory compliance perspective. While the tank rules don't have emission limits in them, they do have pretty clear standards on the gaskets you need to have, the bolted covers, et cetera. So when you have a number of tanks, whether it's one facility or multiple facilities under your oversight, it's really important to have you know, a good plan to manage your tank properties and deck fittings, whether that's a site-by-site thing or a corporate-wide deck fitting inventory. You want to understand what's on your tanks and have programs in place to make sure that when you take tanks out of service or do maintenance activities or anything that could impact, affect, or change your deck fitting configuration, you're able to capture that and update it accordingly, both from a compliance and emission calculation perspective. That means you're going to have consistent emission inventories and not potentially over or under report things. You're going to make sure that you can accurately do NFSS modification analyses should there be changes to those deck fittings, and you know when you may trigger NFSS KB if you're dealing with a tank that's subject to an older standard. There's a variety of reasons that it's not just a construction activity, build the tank and forget about it, but rather an important piece of environmental management information to stay on top of. So that to be said, we've covered the floating roof deck fittings in significant detail. Now we'll look at storage tank compliance requirements for fixed roof tanks with closed vent systems. Not a lot to cover here. We're going to keep it kind of focused on storage tanks, but we don't want to miss discussing you the fact that these are, storage or the closed vent systems are designed to collect the vapors and gases being emitted from those tanks and route them to a control device and prevent them from escaping to the atmosphere before they get combusted. And from the NSPS KB perspective, we want to have no detectable leaks above 500 ppm and look for a VOC reduction of 95% or greater for whatever type of a control device you're using at the tail end of that closed vent system. So then we've talked about design requirements. We'll get to storage tank operational requirements here to kind of talk about some additional elements from NSPS KB as it relates to these storage tanks. And so one of the big questions that comes up quite often is the rule states the process of filling, emptying, or refilling shall be continuous and shall be accomplished as rapidly as possible. Unlike other regulatory definitions, we don't have a lot of clarity or specific guidance on what that means. So a common question comes up as to what does continuous mean? And some of the ways that we can start to define that, or at least build consensus around what's appropriate to account for this demonstration would be, no interruption of filling for pump out once, filling has commenced. So once you start filling or emptying your tank, see it all the way through. Don't, you have your tank at, your tank roof is at 6 feet, you pump in 3 feet of liquid, you let it sit there, and then you come back 2 weeks later to fill it because there was some scheduling issue. That would be tough to meet the continuous standard unless you perhaps emptied it back out. You can start and stop, but can't empty until the roof is floating. Let's see here. Start and stop. I can't. So there are some allowances for, if there is a maintenance issue or other uncontrollable issues. It's not a hard and fast standard, but we want to make sure that once you start the process, you work through it until you get your tank to that in service or out of service state. Right, exactly. Yep. As rapidly as possible is also not well defined. We understand that there can be product scheduling challenges, inventory management. So it's not necessarily an hours game. A 1 to 2 day window between a service change or filling, emptying a tank, or taking it to the next cleaning stage or something to that effect is well within the reasonable, continuous and rapid time. Even giving potentially a period of a week may be acceptable depending on the actions you're taking to empty the tank or work you're doing around it. But if you're getting in that greater than a week period, that's where we run into the, can you defensively say that you are being continuous and trying to accomplish this as rapidly as possible? And, again, there may be some jurisdictional variation, or, you may have to deal with potentially regulators having differing opinions. So we want to have, good plans and procedures in place to make sure that when operations is emptying a tank or doing work on the tank, they understand the requirements and have a plan in place to empty or fill in a continuous manner. Mm-hmm. Correct. Gary brought up a good point that if you're landing your tank and you're going to be moving into the cleaning and degassing phase, and you've emptied it out as much as you can to get to 3 feet, and you're not going to let that sit there for too much longer, you could reasonably consider, you just have to run your standing idle landing emissions for that period of time. Yep. Yep. Mm-hmm. Yeah, if you had to trickle fill it, I would argue that you may want to, from a filling perspective, evaluate if you can batch it to a slightly more tighter time frame. But essentially, yeah, you have to account for your emissions and do it in a way that you can defend as being continuous and rapid. We're a little ahead of schedule at just almost an hour and a half in here, but we can maybe take maybe we can take a few minute break, return at 2:30, and then we'll see how the second half goes and maybe grab one more break before the end here for those that are sticking around for the full time. So on that note, we'll see everybody in a few minutes. Hey, Tony, are you back?
Yes, sir.
All right, we'll get rolling here in just a minute. All right, well, we have hit over our break time, so some folks have trickled back in, so we'll pick back up where we left off. We worked through our regulatory program overview for storage tanks and vessels. We've covered general design requirements for floating roofs, and now we'll start to dive into the air emissions from storage tanks in a little more detail than our morning presentation, and go from there. All right, so for floating roof and fixed roof storage tanks, we have a couple different emission pathways that are both similar and different from each type of tank, and we'll cover these in a reasonable amount of detail. But since we only have part of a day and part of a class, we have scaled it hopefully accordingly. But if you have any questions, please, we can stop and certainly dive in here. So for fixed roof tanks, we have primarily working and standing losses constitute what are referred to as the routine emissions, the general emissions you would expect to see from storage tanks as they're operating. These are based on throughput through the tank and the fact that the material in the tank is volatile and is evaporating. Additionally, these tanks can be cleaned and degassed, so there's another emission calculation method to use there. And then also we have potential flashing losses if we're talking about upstream tanks in the oil production segment, but we are not going to be covering flashing loss calculations in this presentation today. We're going to focus primarily on the AP42 based calculation methodology. And then for floating roof tanks, very similar to the fixed roof tanks, we've got withdrawal losses, or working losses, which are based on a function of the throughput or material handled by the tank. And then also the standing losses, which again are a function of the tank storing material. Additionally, we can have floating roof landing losses. So again, as that floating roof is landed and is no longer in contact with the liquid, we run into a situation where there's a different calculation methodology that results in higher emissions due to that vapor space created below the floating roof. And then when you go to refill the roof, you end up with that similar situation of displacing a pretty concentrated vapor space that can have substantial emissions associated with it. And finally, just like fixed roof tanks, you can clean and degas these tanks, and depending on your emission situation or stored material, tank conditions, how your cleaning process goes, you can end up with pretty substantial emissions from a cleaning situation as well. So again, we've talked about vertical fixed roof tanks. We'll start with these calculations. This is just a good old figure from AP42 to kind of tie together all the stuff we've talked about thus far. Again, external floating roof tanks, we've talked about the deck fittings, the rim seals. We'll dive into the emission calculations here, but this is just a good reference figure. For the floating roof tanks, unlike the fixed roof tanks where we have just a function of liquid going into the tank and being in the tank, our floating roof tank emissions are driven by a number of sources. We have, impacts from the rim seal, impacts from the deck fittings, potentially impacts from the floating roof itself if it's not welded, in addition to the withdrawal losses as that roof moves up and down. And then, of course, we haven't fully distinguished between an internal versus an external floating roof tank, but as Tony noted earlier on, the internal floating roof tank type simply is a combination fixed roof and floating roof, and that fixed roof eliminates the wind effects and therefore can theoretically result in a tank that has lower emissions than an external floating roof tank. So from an emission calculation perspective, there's sort of a general hierarchy or perhaps path to get to where we are today. I guess if you want to refer to it as primary sources of the calculations we are most familiar with, started back in the API MPMS measurement Manual of Petroleum Measurement standards. Chapter 19, and this has sort of all of the nitty-gritty background details in terms of where these calculations were derived from, the empirical data and all that. Unfortunately, they're not publicly available. They're not super expensive, but they're sometimes a challenge to get, especially if you're just trying to find one tiny piece of information. To that point, they have been used as one of the primary developmental tools to get us to Chapter 7, Section 7.1, Organic Liquid Storage Tanks, in the EPA's free and widely available AP 42 guidance document for emission calculations. And so a lot of what is in AP 42 is simply distilled down from the API MPMS documents and publicly available, and what all of our regulators use and what we use to play ball with for the most part in terms of emission calculations. It's the official reference source of tank calculations by most agencies, and it's really what the states and EPA expect to see when we're talking about tank emission calculations. And then from that, right, we have AP 42, and how many people have attempted to look at or read Section 7.1? Some people, a handful of folks, right? It's it's a couple hundred pages of equations, algebra, tables, and numbers, which again, it's not rocket science to follow, even though I wish I could brag about being a rocket scientist, but it's just a bunch of algebra and some numbers. So it's not complex math, but it's complex in the significant amount of equations to manage and to understand how to and where to correctly apply the simple algebra, right? So to that point, historically, there has been an EPA tool, TANKS 409D, that was used sort of as the ubiquitous tank emission calculation tool. However, with the recent updates, as recent as last year to AP 42, that has effectively rendered AP 40 or TANKS 409D no longer effective. The liquid temperature, what's that? Worthless. Yeah, I mean, it was free to begin with, right? So I mean, even less value. Now it could cost you money in terms of compliance fines. So there's yeah. Anyway, so right, we, for a variety of reasons, need to move away from TANKS 409D. If you haven't already, there's intrinsic errors even with the old AP 42 in the TANKS program. We know it doesn't do elevated temperatures correctly, and now it most certainly is not aligned with the new, more accurate equations in the 2020 version of AP 42. So really, aside from potentially historic checking of things, there's really not a place for TANKS 409 in emission calculations moving forward. You can then, go your own route of developing in-house spreadsheets or software applications, or there's a lot of off-the-shelf tools that may exist, either by way of modules to larger inventory management programs, specific emission calculation tools. We, Barr, have developed the Barr tank emission calculation spreadsheet as sort of we identified that TANKS 409 was going to be on the way out pretty quickly a couple of years ago, and realized it'd be pretty easy for us to develop a tool internally to use for tank calculations. And we have created that as a tool that's available. We use it internally ourselves, and if you're interested in using it or seeing a copy, you can sign up for access to that on our website as well. And we'll It was a fun challenge. I'm giving it the sunshine coat, Gary. We're looking at it with rose-colored glasses. But the other kind of big note, right? We've talked about errors with TANKS 409D. Perhaps the next time we present this, we won't even have to reference this program anymore. Spreadsheets offer, for a lot of us, better control because we like spreadsheets, right? I mean, I like spreadsheets. It gives us a chance to be able to change or update or refine how we're doing the calculations without having to wait for a vendor to update a software behind the curtain black box thing. However, it can be challenging to leverage across multiple sites or locations, or repeatability issues, or if somebody makes a really awesome spreadsheet that does your compliance calcs. They leave, they move, something changes. You now have a what somebody thought was a great whiz-bang tool that now nobody else can decipher or understand. And that can be a challenge as well. So their spreadsheets, are good, but there's definitely some challenge with, understanding how to audit or detect errors in those calculations, especially if you don't have things locked down. Our calculation spreadsheet tool is locked down in that you can't edit or change the equations and inadvertently delete something that could result in an issue. The other kind of flip side to that, right, is a more traditional software application, whether it be an Access database or a more shiny, polished tool of some sort. The challenge here, and we've seen this in several different vendors' tanks emission calculation module, is they're very black boxish in that stuff goes in and you get numbers out, and the numbers might be of the right order of magnitude, but it's very hard to audit the intermediate calculations, which we'll kind of look at in a minute here, and know that, okay, I put in my throughput, my temperature, my vapor pressures, and I have emissions. Okay, that tracks, but was there a goofy issue with how the vapor pressure function was calculated, or how an elevated temperature is being applied? And if you can't test that yourself, if you can't see those things, you need to really talk with whoever's providing you your tank calculation tool to get those questions answered, because it may not be an issue today, but when you have an issue down the road or an inspection and your inspector is either curious about tanks or suddenly has become aware about tanks and wants to understand how you're calculating them, and they look at AP 42 for 5 minutes and see it's 1,000 pages, a couple hundred pages long with a lot of equations, they're probably going to have questions. So if you're not able to easily answer those, that can be a bit of a concern. In AP 42 itself, they say that you can use spreadsheets or software applications, but make sure you trust or you test and verify them, because we're not going to certify or approve anything. So I'd be cautious if anybody says they have an EPA certified or approved tool, because effectively there shouldn't be or isn't one. Not to say that it's not correct, but something to be aware of. So again, can you work examples by hand, get comparable answers, just some notes on calculations. So again, we've talked, right, we're talking specifically AP 42, chapter 7.1. We want to use tools that accurately apply the equations, whether it's a spreadsheet or a program. The updates were published, if you've been following along, initially in November of 2019, and then there was a final publication in June of 2020, which really just incorporated a few administrative clerical updates and issues, not anything of technical substance. That was really captured mostly in the 2019 update. This included a lot of changes to the temperature equations. So for our liquid surface temperature, for our bulk liquid temperature, that's really where the most substantial change occurred in how those equations went from assuming a shell height over diameter ratio to a tank-specific shell height over diameter ratio, which is good because it's more accurate and there's some advantage to it, but it also creates added complexity, again, in the calculation methodology. If you're doing it by hand, you run into making sure, have you organized your calculations and aligned the calculations correctly with the type of tank that you have for the emissions that you're trying to calculate. The other challenging bottom line is the change to AP 42, the pile of new equations doesn't appreciably change the bottom line. I think we see, give or take, about 5% one way or another in emissions change, which is not nothing, but it's also not typically enough if we're talking about tanks to put somebody in a different source category. But it's also just enough to be substantial enough where we have to go through the effort of making sure we've got our numbers accurate and calculated correctly. And then finally, we have the added inclusion of cleaning and degassing methodology within AP 42 itself. I mentioned the API MPMS documents a few slides back. That covered most of the routine and non-routine emissions, but that also did not include tank cleaning emissions until boy, 7, which I guess really is still kind of a long time ago, but it was under a technical report, and it just kind of, from my understanding, sat there for a while. Some people were aware of it, people were talking about it, but it really wasn't picked up by regulators or seen as a major issue outside of Texas, outside of some other key jurisdictions. So tank cleaning and degassing emission calculations have been more of a concerning topic in the last few years, now especially that they're specifically included in AP 42, and there's a publicly generally available calculation methodology out there. The cat is to some extent out of the bag in that sense, and if we are not permitting them or including them from a PTE perspective, there's at least at minimum the need to reference them from the actuals emission inventory perspective. I've talked about tanks 490 being terrible for enough now. We don't need to belabor that point. Some other changes from AP 42 to the new one. There's a new meteorological data set updated with multi-decade averages, and on average, they are all a little bit warmer as well. So again, if your facilities that you're working with or using rely on the AP 42 default meteorological data, you're going to see, with nothing else changing, likely an increase in your TVPs from a compliance perspective, which will ultimately bump up your emissions some as well. Additionally, another challenge, again, these are all, I think, generally applicable, but really important if you're very close to that 11.1 PSI threshold. If you're relying on AP 42 meteorological data, that's getting a little bit warmer. If you're using your paint coefficients, the AP 42 paint coefficients used to be good or poor, and now we have new, average, and aged paint coefficients. And what that's doing is it's taking good is analogous to new and poor is analogous to aged, and average is the average of the two. This layout existed in the API documentation historically, and now is aligned in AP 42. And it's not a huge difference, but if you're especially dealing with a tank that is not painted white, and you may not be able to confidently assert that your paint condition is new and your alpha is now going to be aged, coupled with the mild increase in meteorological data, a slightly higher alpha coefficient, again, overnight, nothing changing, you may end up with a higher vapor pressure without being directly aware of it. Now, if you maintain your tanks painted white, you have some other things in place, you could certainly develop a case to continue to use the new paint coefficient. But again, these are sort of not super critical unless you're very close to that vapor pressure threshold, in which case little things can make a big difference. Okay. Oh, interesting. Okay. Sure. I haven't run across that myself. Anybody else heard any recent news on meteorological data impacts? I mean, the other note too is, from a compliance perspective, you could also consider using current meteorological National Weather Service data as well. Granted, that has some challenges with it also, and can be more difficult from a permitting perspective. So that's good context to have, and we'll have to keep an eye out for that as well. Another interesting change, again, to align with the API documentation into AP 42 is floating roof rim seals now have two categories of tight fitting and average fitting. And we've scratched our head around the tight fitting representation because there's a little bit of guidance in AP 42 around what this means, and a little bit of guidance, not even guidance, but description in the API documents. And the concern is, how can you confidently demonstrate that you're constantly always going to be in the tight fitting rim seal category? One thought is, if you're an EFRT and performing EFRT-based seal gap inspections and constantly meeting and demonstrating compliance with those, that could be one avenue to pursue. But from a bigger picture, using the average fitting deck fitting coefficients, which were in the previous AP 42, aren't going to change your deck fitting, or I'm sorry, rim seal emissions, and it's one less piece of information to manage or try to demonstrate compliance with. So if you get curious about rim seal emissions and see that there is this, tight fitting category, yes, it does exist. Yes, it will show that you have lower emissions, but be cautious moving forward if you want to effectively claim that as being a useful coefficient, because there's definitely a burden of a proof that you'll have to develop to demonstrate that that's okay. And again, there's, oh, Gary? Yep. That is a thought. We haven't tested that in the regulatory sphere outside of discussing it. The bigger challenge would be on an IFRT or a domed external floating roof tank, because do you really need to, well, you don't have to test those seals to begin with, and do you want to attempt to go above and beyond to test rim seals in a covered floating roof tank? So the jury is still out on if that is really valuable. There may be some future, I'm hesitant to say this is more on the speculative side, but there could be maybe a backed layer angle to it. But again, I think this is still pretty fresh, so I don't want to go too far down that speculative road. So things to be mindful of. So we've touched on the tank cleaning stuff already, and then we've got the tank calculation, or the temperature calculations, which we'll dive into in a bit here as well. So we'll start with fixed roof tanks, right? We've got working losses, standing losses. That gives us our routine fixed roof emissions. Relatively straightforward to start here. So now, like, it's the afternoon. We've all had lunch. I have a select number of equations to kind of dive into. Again, Gary, this is beyond the basics. We gotta climb up a little bit here. So we, again, I don't have every single equation from AP 42. I don't think we need to go into express detail, but to appreciate some of the new calculation changes and understand a little bit more all the stuff that Tony covered beforehand, all the stuff up to now, we'll dive into a few numbers, or at least formulas here to get a better perspective of what that looks like. So right, we've got the fixed roof standing losses are a function of the material in the tank. So whether it's a tank that's constantly turning over or just sitting halfway full for a month. We have an equation based on the number of days that the tank is effectively in service for that period of time. And then there's a number of factors and coefficients that go into determining what that evaporative breathing standing loss is from the tank. So whether the temperature cycle is influenced by the diurnal temperature change, so the day to night heating and cooling, or you have a heated tank that experiences temperature cycles, as that vapor pressure increases by whatever method you're heating the tank, or the tank is being passively heated, we're calculating the density of the vapor, the amount of vapor in the tank, the expansion factor, which is effectively how much gets pushed out, and what that pushed out vapor, how saturated that is. Typically, we look at it on a number of days, but in heated or insulated tanks, that number of days becomes more so the number of heating cycles. So if you have a fully insulated tank, you're insulated from the ambient temperature impacts, and you then have to rely on how many heating cycles does your tank go through, and that drives your cyclical temperature evaporative losses from the tank. So to just dive into a little more clarity too, we're talking about a fixed roof tank, which is perhaps a more simpler geometric, it's a cylinder, right? However, we have to be conscious of the fixed roof geometry, because that adds to potential vapor space that can be saturated with VOC. and then also understand, are we talking about a vertical fixed roof tank or or I'm sorry, we're not quite there yet. Do we have a dome or cone style roof? All that geometry plays into what that vapor space is inside of your tank that can be emitted to the atmosphere through this standing or breathing loss scenario. And there's different equations depending on the height of your, the style of fixed roof you have, whether it's a dome or a cone. It's just some geometry to get you that volume measurement. Horizontal tanks, right? When we talk about fixed roof tanks, I almost always default to thinking about an upright cylinder, traditional fixed roof tank like the figure we had a few slides ago. However, for a horizontal fixed roof tank, HFRT, we do have to do a couple manipulations to the calculations to get that to work correctly. So when we get information on a horizontal fixed roof tank, we're typically given the length of the tank and the cross-sectional diameter, which is useful in most regards. However, from an emission calculation perspective, we have to essentially reorient that given diameter and length to the effective length and diameter to turn our cylinder tank on its side to an equivalent vertical tank of that size. So we're doing some geometric manipulation to get an equivalent diameter and height to then use for those horizontal calculations. Again, that's and then for a horizontal tank, the DE, effective diameter, and HE, effective height, get used in place of diameter and height in all of the other fixed roof calculations. Again, so the vapor space expansion factor is another, I don't want to say popular or exciting equation, but it's one that has several different iterations in AP42 that range from very complex to, if you have no other information, you can assume KE is 0.04. So that may be good for ballparking, but unfortunately, in today's world, if we're doing tank calculations, we're probably already using a tool that will calculate it for us anyway. But again, this is a representation of how our vapors within the tank are going to expand based on the vapor pressure of the material and the temperature effects on the tank. So we're looking at the temperature range of the vapor space, the liquid surface temperature, the atmospheric pressure, the pressure of the vapor pressure of the material. If we have breather vent settings, all that goes in to calculate KE. And typically this is the most appropriate one to use. However, it's also the most complex one to use because you have to calculate a range of vapor pressures and a range of temperatures to effectively calculate that. The other KEs, if you assume tank colors, if you assume a couple other things, you can get more simplified versions of the equation. But in today's calculation age, if you've got a spreadsheet or a tool, you might as well rely on the most accurate and representative calculation to do that. So here we end up TV the vapor temperature range is a key variable here, and this is the new representation in AP42 for the daily average vapor temperature. And it's a lot, but it's driven by the fact that we look at the impact of the tank shell ratio or tank height over diameter ratio, and that allows for a more accurate representation of the thermodynamics that are impacting the tank. So again, it's more accurate, which is better, but it also is more work to get set up right. Especially if you're trying to create something from scratch. The old AP42 relied on a default HS over D ratio of 0.5, which industry-wide average is not unreasonable, but it definitely, if you're at either end of the spectrum, you can have, there's going to be some winners and losers. But this again is a beginning kind of dive into the, we're also looking at the solar absorption of the roof and the solar absorption of the shell, and all that works into the overall equation there. So then this is for an atmospheric tank. If we partially insulate the tank, suddenly it becomes significantly easier, and we have just some theoretical thermodynamic heating impacts from the solar gain through the roof. If we have a fully insulated tank, like I was saying earlier, that goes to zero, and we end up having to rely on, again, the temperature cycling from the calculations, or from the heating cycles. So that, again, is a flavor of the temperature calculations that go in, the new temperature calculations that go into the emission calculations. The other big one that somewhat persists from AP42 in general is the vapor pressure calculation. Of all the calculations that we're talking about, whether it's fixed roof tanks, floating roof tanks, non-routine events, right, the vapor pressure of the stored material is going to be one of, if not the most significant differentiator between why one tank has 10 tons of emissions and why one tank has, 0.1 tons of emissions. True vapor pressure, the liquid surface temperature. This is the PVA for petroleum stocks. There's an A and B coefficient. Typically, these are based off of a Rankine, or I'm sorry, an RVP measurement that's converted to a coefficient. This equation overall hasn't changed. Again, the big change, though, is in the liquid surface temperature that we'll look at in a minute. A big note, though, to make sure that even if you're using the latest and greatest AP42 calculation methodology and you have tools that are implementing the calculations correctly, there's still kind of the lingering specter of bad vapor pressure coefficients from the old AP42 or other sources. Specifically, the most significant one was the number 6 oil issues with some terminals in the Northeast, where they were using old, incorrect, artificially low AP42 vapor pressure data for number 6 oil, and also using incorrectly applying elevated temperature calculations to those emissions. So they had artificially low emissions. They didn't have a permit when they needed one, and bad data contributed to pretty significant NOVs all around. So even if you're doing the calcs right, we need to continue to make sure we have a strong handle on, is what we're putting into the equations, good. I mean, I'm not a modeler, but the mantra of garbage in, garbage out is certainly applicable even to these type of equations, where if you've got questionable or uncertain vapor pressure data, it can be it can cause problems. So again, here we have the liquid surface temperature using the specific HS over D ratio. It's a weighted impact of the ambient temperature, the bulk liquid temperature, and then thermodynamic solar gain to the tank. And so this is what we have, to work with in AP42 now. But just for context, if we assume the default ratio, it becomes very simple. Again, what we're doing is, and the way that it perhaps makes a little more sense is, instead of relying on default coefficients, we are able to specifically calculate them now per the tank that we have, which can generally be a good thing. So we've been, up until this point, talking about the liquid surface temperature, which is a bit of an abstraction and probably worth another slide or two. If you've ever had to have detailed conversations with your product group or anybody else on potential concerns about vapor pressure exceedances, talking in liquid surface temperature can be challenging because it's potentially a bit of an abstract concept to groups outside of the environmental side for tank calculations. Most of the time, right, when we're talking about tank temperatures, everybody defaults to the bulk liquid temperature or the average temperature of the stuff in your tank. And that's what we'll get into in a second here, but it's important to know that when we're dealing with vapor pressure calculations, we're looking at the liquid surface temperature, which is that interface between the liquid and the atmosphere, or the liquid and the roof. And that can typically be a little bit cooler than your bulk liquid temperature. But that can also, you need to temper that with saying, oh, we have actually a little more room on temperature, because they can kind of go crazy and run with that and think, oh, we can run the tanks hotter now, or things like that. So there's a little bit of a strategy involved in managing temperature, especially when you're talking to groups outside of the environmental realm. Okay, so bulk liquid temperature. This is a little easier, right? If you can measure it, use that. That's the easy bottom line, make it simple. You probably have, or you or your clients probably have thermocouples in the tank. Get the average temperature for the tank for the month. There is your bulk liquid temperature. Otherwise, for fixed roof tanks, for uninsulated fixed roof tanks, it's a pretty simple calculation. But again, if you've got measured temperature for the bulk liquid, it just makes sense to use that. There's a whole bunch of other calculations that were included for the standing losses of a fixed roof tank, the saturation factor, the vapor density. There are a whole bunch of other ones that, again, are iterations of the ideal gas law and other essentially concentration calculating equations that exist. We don't need to dive into them here. Like I said, we're not going to go through all of the calculations, but it comes as someone who may be responsible for air calculations or overseeing people doing air calculations. How do you have confidence or accuracy in making sure that from start to finish everything is being done correctly? And a software model or something that's locked down is a lot easier to audit or understand if you've got if you just have to worry about the inputs and the outputs, and you know that your intermediate steps along the way are okay. But again, just some considerations there. So then we'll shift gears to the working loss angle now. So that the standing losses are driven purely by stuff being in the tank, being affected by the ambient temperature acting on it, or heated heaters. For working losses, this is going to be primarily driven by throughput. And for a fixed roof tank, we have liquid going into a tank. That liquid going into the tank raises the liquid level, displaces the vapor above it, and we have emissions generated from that rise in the liquid level. When you empty the tank, you pull the liquid level down, it draws in fresh vapor. There's no emissions associated with that activity. So again, we have the kind of the primary, what's our throughput driving that liquid level change? And then we have some turnover factors, some product factors, vent setting correction factors, all of these to, again, dial in the accuracy of the amount of vapors being expelled from the tank. From an important concept perspective, how are you calculating or quantifying throughput? The best way to do it is to rely on level data to get your actual liquid movement to then calculate throughput from that. Or are you, again, when we look at tanks, over time, throughput in typically equals throughput out. But if you're looking at, really only a monthly calculation for fixed roof tanks, we really want to be interested in the throughput going into the tank because that is associated with the liquid level increase. Again, vapor pressure is another key variable throughout the equations. And the pressure and vacuum vents can assist in limiting emissions. Some tanks have a breather vent and vacuum setting, a couple, a fraction of a PSIG one way or another that can limit emissions a little bit. I haven't seen anyone ever try to claim a significant amount of control by way of a breather vent, but typically they're on smaller tanks storing perhaps a pharmaceutical product or some other organic chemical outside of the fuels world. And so again, your pressure vacuum vent settings can impact you can reduce your emissions. So now that's the overview of fixed roof tanks. We'll now shift gears into the floating roof tank world. And very similarly, I think we've used working losses and withdrawal losses somewhat interchangeably. The same with standing and breathing losses. The old AP42 had a general use those terms interchangeably as well, but really when we're looking at total emissions from a tank, there's the working component, whether it's fixed or floating roof, and the standing component, whether it's a fixed or floating roof tank, and there's some differences now that we'll dive into on these tanks. So for the withdrawal losses from the floating roof tank, and I use withdrawal losses here purposely because unlike the fixed roof tanks we were just talking about, with a floating roof tank, the throughput that we're most interested in from a withdrawal loss or working loss calculation is the outbound throughput or throughput associated with a reduction in the liquid level and a reduction in the floating roof height. So as you pump oil or gas or what have you into a floating roof tank, you're raising up the liquid level and covering up the interior shell of the tank. As you pump liquid out of the tank, you're lowering that floating roof, you're exposing a thin film of material on the inside of the tank, that evaporates, and that is the effective loss method for withdrawal of working losses for a floating roof tank. Whereas on a fixed roof tank, our working loss method or function is displacement of vapor space with an increase in liquid level. So to that point, right, we have a number of other impacts or items around clingage factor, how much, how rough is the interior of your shell? Is it going to hold more oil or not? Your liquid density, there's a conversion constant, number of fixed roof support columns. So if you have a internal floating roof tank that is not self-supporting and has a number of support columns, whether it's 1 or 20, all of those support columns, in addition to the shell, will have that wetted perimeter happening and will impact or increase your withdrawal losses as well. Curiously, the withdrawal losses from a floating roof tank are not as directly impacted by temperature and vapor pressure. One could argue that the density of material is most certainly a thermodynamic property and does vary with temperature, but in terms of the accuracy and information we typically deal with, we're dealing with one or two density representations for the 1 or 2 products we may be storing. So really it comes down to what's your density, and we're not too concerned with our density at 25 degrees Celsius versus our density at 60 degrees Celsius, because for most of our stuff, we're talking a comparable order of magnitude, not enough to appreciably change this. I'm not familiar with folks that have dived too deeply into super specific density representations in their withdrawal loss calculations. But what's that? Excellent. So again, from the withdrawal loss perspective, we're really concerned about throughput and density. Obviously, the size of the tank is important, but that's kind of, once you build the tank, you build the tank, and can't do too much with that, at least as far as I've seen. And then, of course, the number of fixed roof support columns, should you have them, will also impact your emissions. So then we shift to the standing or breathing component of floating roof tank calculations, and we end up with a little, a slightly different ballgame compared to the fixed roof tanks, because we have 3 components that make up our standing losses. So there's the deck fittings, the rim seal, and the deck seam losses. And the rim seal is based on, do we have a primary or secondary seal? And then the deck seam losses are based on, is your floating roof welded, or is it bolted, or some other way not fully sealed? So from a deck fitting loss perspective, all the things that Tony and I talked through at the beginning of the presentation in that deck fitting section effectively have an emission factor calculated. So whether you have an access hatch or a roof leg or a vacuum breaker, each one of those you effectively have to go through to determine the total deck fitting loss per month based on the number of deck fittings in each group and the emission factor associated with those deck fittings. And it's not just a one factor to one deck fitting, it's based on the vapor pressure, stored material, vapor molecular weight of the material in your tank. So it's again, not overly complicated calculations, but it becomes challenging in the repetition to calculate your emission factors for all of your deck fittings for your entire tank, and then making sure, if you're so bold as to set up your own calculation tool, making sure you do something in a way that allows you to repeat this calculation accurately and quickly, essentially. So from that deck fitting loss, the total deck fitting loss, like I mentioned, is based on the total number of deck fittings, the vapor pressure of the stored material, and a product factor. We then have to calculate the individual loss factors per deck fitting per type. And this is the first area where we see an impact of, if you're a fixed roof or a floating roof tank, I'm sorry, an internal floating roof tank or an external floating roof tank, we see in the KV factor, effectively there's kind of 2 main parts to the equation. And this second part here is the wind-driven effects component. And if you have a covered roof tank, that effectively goes to 0. Again, not to go through all this, but it effectively for each deck fitting, we calculate an emission factor that feeds into the overall deck fitting emission factor calculation. An AP42 has kind of two things. One is obviously the specific factors that you use per deck fitting in each type of category. For access hatches, you can have a bolted cover and a gasketed access hatch, an unbolted cover, ungasketed, so on and so forth. And this table also, we didn't talk about design considerations too much, but AP42 does have some useful information around evaluating the size of a tank or the type of a tank you have if you don't have a lot of good design information yet. But it's very dangerous to, or not dangerous, but you want to be careful in using it beyond preliminary screening purposes, because the estimated deck fittings in AP42 based on the size of your tank are based on average vendor information, and certainly may vary from the folks that you're using to help design and build a tank. So it's a good kind of benchmark to do some rough calcs. But if you're into the actual permitting stage, you really don't want to be relying on default deck fittings, default anything really today. There's a lot of challenges that can come with that. So as we're talking about deck fitting losses to kind of close out, again, the stored product and temperature are going to influence the vapor pressure. Having an accurate deck fitting inventory, that apparently we talk about that a lot in this presentation, but here's kind of another instance of where that shows up in terms of what are your deck fitting impacts going to be, and do you have the correct controls represented in your counts? You can see here that the first coefficient gives you the order of magnitude around what your emissions may be, and the biggest one is especially those slotted gauge poles. If you have an uncontrolled slotted gauge pole, that's going to be a tremendous source of standing emissions for your tank. If you have a controlled slotted gauge pole, it's still going to be noticeable, but it's not going to adjust the order of magnitude for those emissions. And then finally, is the floating roof covered or not? That'll again impact the wind effects. So then we'll jump to the rim seal losses as kind of the next evolution of emission calculations for floating roof tanks. And similar to the deck fittings, we run into a situation where, based on the type and style of seals, we have certain parameters, and then it's just a function of the diameter of the tank, the vapor pressure, molecular weight, and a specific product factor. So we're looking at what's the type of rim seals that we have, what is the vapor pressure and chemical properties of the stuff that we're storing, and how will that impact the bottom line of our emissions. Again, AP42 has a seal or a table of rim seal factors. The average fitting table is here. There's both welded tanks, and there are apparently somewhere a few riveted tanks that still exist, probably in the Cushing area. Some of the older operators still have those 1950 era, maybe pre-World War II tanks that may be riveted and have factors that still exist. But again, these factors work into that equation and ultimately give us our rim seal losses. One other equation that showed up kind of in these recent equations is the vapor pressure function, which is a relationship between the atmospheric pressure and the true vapor pressure at the liquid surface temperature of our stored material. It just kind of expanding on it here, used throughout the equations. Again, from an ideal gas law perspective, it's used to develop that relationship and then support the evaporative loss calculations for the deck fittings or rim seals or what have you. So here we get to, again, the average liquid surface temperature. And I could not bring myself to type these out or even ask somebody to type them out for me. So I just grabbed them from AP42 to prove the point that I think we've all come to realize is they're long, but that doesn't mean that we don't need to be aware of them or know how to use them correctly. So this is the average liquid surface temperature equations for floating roof tanks. So we have one equation up here for internal and domed floating, or internal and domed external floating roof tanks. So if your tank has a cover on it, that top equation is how you get to your liquid surface temperature. 7 miles long, but again, all it's doing is developing the specific coefficients for your ambient temperature weight, your bulk liquid temperature weight, and your thermal or solar gain weighting. And very interestingly, for external floating roof tanks, we have the steel pontoon style floating roof tank and the steel double deck floating roof tank. And very curiously, there's a pretty significant flip-flop between the weight of your ambient temperature to the weight of your bulk temperature. And this can be another scenario where you run into having or experiencing a significant change from old AP42 to new AP42 in how your emissions are going to, or how your vapor pressure is going to shake out. From your emission perspective, it'll certainly have an impact, but where we've seen it most shockingly was in the TVP calculations for demonstration, where suddenly we had tanks that had, were really pushing the envelope for TVP compliance. And if we have a white external floating roof tank that's receiving hot stock, there's a pretty significant cooling effect that happens based on the weight of the ambient temperature to those tanks. Conversely, tanks that have a double deck roof it's almost like pseudo insulation in that the bulk temperature plays a more significant role in influencing the liquid surface temperature. So I think we've already hit this, bulk liquid temperature, measure it if you can. Otherwise, there's another family of equations similar to these that go through how to correlate your bulk liquid temperature or how to correlate ambient temperatures to bulk liquid temperatures. So essentially, you're working backwards from equations like this. The other concern here is, again, if you're receiving hot stock we don't often see fully insulated floating roof tanks. Excuse me. We do, however, often see floating roof tanks that are receiving hot stock or material coming through a pipeline that has experienced thermal gain through high pipeline rates, or material coming off a process unit. There's going to be, you may not really be an ambient tank because of that elevated temperature material coming into the tank and depending on how quickly it leaves the tank. So by using measured bulk temperatures, you completely remove the ambiguity there and have your bulk liquid temperature. But if you're relying on the AP42 algorithmic equation to go from ambient temperature to bulk liquid temperature, there needs to be some concern, or not some concern, but there needs to be some confirmation that you're actually an ambient tank and not just inadvertently storing higher temperature material. Unknowingly, or the final deck fitting, or I'm sorry, the final floating roof a standing loss category we have is a sometimes category. Again, it's deck seams. So if we have, Tony mentioned the floating roofs, the aluminum skin and pontoon style floating roofs. Those can have like a thermal weld, but they can also be bolted or riveted. So we have those aluminum panels that get put in, aluminum foam panels that get put in and are bolted or otherwise fastened together and are not a impermeable seal. And much like the rim seals, the deck fittings, everything else we talked about, there is some amount of evaporative loss through that deck seam. And for welded tanks, again, we're just playing with algebra here. So if it's welded, we have a zero term in there and it goes to zero. We don't worry about deck seams. But if we have a tank that does not have welded seams, we have to look at what is the area of those non-welded seams, and that works into there's a coefficient for the factors, and we end up with calculating the emissions from that unwelded seam space on the floating roof. So we've covered the primary emission pathways for fixed roof and floating roof tanks. We've also talked about EFRTs and IFRTs and DEFRTs. And I think historically, right, we would look at IFRTs or people would consider IFRTs potentially as backed with the covered floating roof and your wind-driven loss factors being eliminated. However, it's going to depend on tank design, and certainly with BACT too, there's cost and design components as well. But depending on the rim seal configurations, the deck fitting controls, the size of the tank, the number of the fixed roof support columns, the number of roof legs, and a number of all those factors that we talked about, BACT may favor covered floating roof tanks. However, depending on the stored material, the project, and the availability of flexibility in design, there could be scenarios where you have better performing EFRTs as well. So and if you don't want to necessarily go down the covered floating roof tank route, you may have some options to consider beyond just the floating roof or the covered floating roof tank. I think Tony noted this kind of at the top of the discussion here. Flashing emissions are another category. Typically, we see those from unstabilized crude oil in the upstream industry. By the time we get to the tanks and terminals that we've been talking about here, though, that has either flashed off, it's been weathered, it has been processed, or we're dealing with refined products. AP42 itself doesn't deal with flashing losses. If you have unstable material that's boiling or volatile, there are other process simulators, sample analyses you can run to better account for those emissions beyond the equations that we've just been talking through, because those certainly will not cover those. So that is the routine section of emissions. I'm going to stop to catch my breath for a moment. Any questions quick on that before we press on into the non-routine elements here? All right. Hey, Tony, did I miss anything, or everything sounded good from your end?
Nothing's coming.
All right, so now we'll be shifting gears to the more non-routine category of emissions. We're talking about roof landings, refilling the tanks, and anything that would be considered non-routine. So we'll start with the floating roof calculations for landing events. Whether a tank is landed on its legs or floated, we have different emission calculation methods to use. Typically, we don't see emission controls associated with roof floating, or I'm sorry, the floating roof doesn't act as the control device in these scenarios when the roof is landed or being refilled. So we have to look at our emission calculations a bit differently here. And to that point, typically, we will definitely see emission controls from the tank cleaning perspective, but I have not seen too many clients that have actively pursued controls on their landing or refilling calculations. I'm not sure if you guys have seen on the land or the refilling stuff or landing or, okay. Sure. Texas asterisk, that's a. I should know better by now that as soon as I say don't see it too oftenly, Texas is the answer. But again, we've got roof landings, tank refillings. That makes up the colloquially coined landing losses, even though we have refilling as part of that. So again, similar to the other equations, there's a litany of calculations based on, are you an EFRT, an IFRT? Do you have a drain dryer, cone down bottom tank? Is it a partial or full liquid heel? What's left in the tank? What's your clingage or appreciable volume? What these end up being are modified breathing loss and rim seal calculations. Limits calculated for maximum total emissions based on what's remaining in the tank also exist, so you can't over emit based on what's remaining in your tank. Oh, now, okay, that's a fair point. The limits that are calculated are tremendous compared to what we actually see in terms of actual emissions from those events. There's kind of the filling loss has kind of two general components. And it's a representation of the vapor space below the floating roof being displaced, similar to the fixed roof tank, analogous calculations. There's arrival losses, and that's based on the stuff in the tank getting pushed out, as well as generated losses that are driven or created by the new material going into the tank. If it's gasoline being refilled with gasoline, effectively it's all one thing. But if it's if you have two slightly different products, you effectively look at what was in the tank and then what is being put in the tank through the calculations. Again, saturation factor, tank type, materials impact the overall emissions for these events. Again, like I said, AP 42 has a laundry list of calculations to go through the landing and refilling calculations, very similar to the floating or fixed roof tank calculations that we already walked through. So we're just kind of keeping this a little more high level. In terms of important landing and refilling topics, the key variables, right, are the number of days, how long was your tank on its legs with stuff in it, were you days or your weeks, what is the volume of the stuff in the tank, and what is the volatility of the material in the tank. We often talk about using a cutter stock or some sort of distillate blanket material during the cleaning process, but in all actuality, you could certainly use that to knock down emissions and vapor pressure of the material in your tank when it's landed before the cleaning process officially begins as well. So that can be another way to potentially mitigate odors or emissions from a landed tank. Again, we talked about the must be accomplished as quickly as practical as we're transitioning from in-service to out of service or back into service. To tie a few things back to the regulatory and permit world, records must be kept of landing events. This is one that we find to be a sticking point and wanted to highlight here. When a tank is going to be taken out of service, we typically have long-range schedules. We understand when those are happening, but then there are the inadvertent operator overnight roof landings that even when those happen, we still need to have those tracked and accounted for from an emission calculation perspective, and the fact that we've got the regulatory burden of keeping records of those events. More interestingly and more challengingly for these non-routine events, unlike emission limits on the working and standing losses, since these are somewhat non-routine by nature, variable in length, hopefully are predictable, sometimes may happen unexpectedly. If you have emission limits, understanding are there going to be concerns with those? And then also what we've seen too is, do you have an event number limit? Can you only land your tank X number of times in a given period? And that gives you some latitude on emissions, but rather how will that impact your operational plans if you're inadvertently land the tank or do a service change or do some sort of a mixer maintenance, yeah. Yep. Per tank or per group of tanks. So they may be more of a emission unit group has a limit on the number of landings as opposed to individual tanks. That's a good point. Most of the time when we're talking about tank limits, we're looking at groups of tanks or facility wide. That's a good point of clarification. And Gary, you kind of answered this one already. Just because you take a tank out of service and land it doesn't necessarily mean that you stop emitting, but you then just have to account for those emissions appropriately and make sure that you've emptied your tank to a reasonable state or begun cleaning it in some capacity. Yeah. Correct. Yes. Yep. Drain dry is the tank configuration, the tank bottom configuration. Drained to puddles is the NFSS KB standard of get it generally empty, but not like eat a sandwich off of it clean. Yep. And again, right, stuff left in the tank, how long till cleaning, those are all some factors. Oh yeah. Depends. How drain to puddles can be a little subjective, right? Yep. Right. Yeah, and that's The other angle is, drain to puddles, or drain dry effectively means that you should only have limited cleanage remaining. And if you look at the standing idle calculations, they're going to be pretty minimal or go to zero relatively quick if you have truly a drain dry tank compared to. Yep. Mm-hmm. Correct. Yep. The challenge, and I think this is always the big issue, is if you have a drain to puddle scenario or even a drain dry tank, but there's something lingering in the sump or even a pocket of sludge or something, there still may be odor issues. Even if on paper our emissions are zero, we have to deal with the reality of what's left in the tank and how that's behaving, whether that conforms to our calculated model or not. There's. Mm-hmm. Mm-hmm. Extra homework for the latecomers. Extra homework for the latecomers. Pivoting slightly, but staying in the non-routine category, we get to the cleaning and degassing events, which again, right, we've kind of sandwiched those. We land the tank, we pump it out, we're standing idle with some amount of stuff left in the tank. Emissions are generated from that activity. We then transition to the cleaning and degassing, where we have vapor space purges and continued forced ventilation. Those, a challenge we've seen working with clients to help understand and quantify these emissions are, as we talk with their tanks group and understand what their cleaning plan is, there can be many different cleaning parts, but from an emissions calculation perspective, there are really only two things that we're concerned with. And one is, how often are they going to use forced ventilation, and when do they turn on and off the fan? To that point, if a tank is standing idle and it's being cleaned, if people are squeegeeing it out, but there's no fan or blowers running, effectively we're still in that standing idle phase of the tank is just open and evaporating to the atmosphere. Once we put on the fans and blowers to assist in that degassing process, then we transition into the cleaning and degassing emission calculations from AP42 phase, where we have to calculate things in this new methodology. And there's two primary parts to that. One is the vapor space purge, which is when you flip on the fan for the first time, you burp out a concentrated vapor space from underneath the floating roof tank. And then you have the continued forced ventilation, which is the ongoing measured emissions from that rich vapor stream being exhausted from the tank. And theoretically, once you get through all your cleaning process, you have a nice clean tank, and as long as it stays clean, you don't have any emissions, and then you refill it and you're back in action. So to that point, the vapor space purge is based on, again, ideal gas law calculations, essentially. What is that concentration of material under your tank? And this, even though when we get to the continuous forced ventilation emissions, this one is not based on measured quantities or fan rates. I mean, if you have a measured vapor pressure data for the material in the tank, you can most certainly use that here. But this is really just driven by, similar to the other tank calculation parameters, what was in the tank, what's the temperature, what's the vapor pressure, that's being exhausted out when you turn the fan on. If you're venting overnight, you effectively only have to calculate one vapor space purge when you first turned on your fans. And if you're continuously venting, you don't have to worry about vapor space purges anymore. If you turn your fan on and off overnight, you then potentially have to consider the impact of a vapor space purge each day you turn the fan on. As your tank is getting more cleaned and going to hopefully clean or zero, there can be some latitude in understanding, do you literally have a vapor space purge every single day, even if you have almost nothing left in your tank, because those vapor space purge emissions can add up to pretty significant numbers when your forced ventilation emissions may be pounds a day. So there can be some incongruity between is your vapor space purge accurate or is your monitored continuous ventilation representation more accurate, and how do you square that circle? So that's fortunately, unlike a SEMS rule or other stack testing based program, there's not a lot of specificity in the tank cleaning calculation procedures. So if you're consistent and do it in good faith, you can figure out what works best for you. But yeah, so that's the vapor space purge, and then once that fan is turned on, we get into sort of the uncharted territory of needing to monitor your emissions, or monitor the vapor space or the vapor concentration coming out of the tank. And this is the arguably newest equation, and certainly one of the more, I don't know if emission calculation equations can be controversial, but certainly challenging, certainly challenging in, this requires us to monitor the concentration coming out of the tank during that forced ventilation process, and also use the ventilation rate, which can be, depending on the vapor pressure of the material, the amount of material, the duration of the project, this can most certainly be a pretty substantial quantity of emissions. But the bigger challenge isn't necessarily dealing with the tons of emissions, but rather how are we going to coordinate monitoring and collect that data consistently, and can we monitor a few tank cleaning events and then apply that general knowledge to the rest of the tank cleaning events, or do we have to monitor every single one, and what's going to be the best approach to do that? That process is still being, I think, evaluated by clients. Some folks have been for years monitoring their cleaning and degassing events. Other folks have been very slow to peel back that curtain to understand what is or is not going on with their forced ventilation emissions.
Way more than the factor of full area.
Mm-hmm. Sure. Mm-hmm. Oh, wow. Sure. Mm-hmm.
Really hard. It would take a lot of data.
That and with the infrequency in tank cleaning events, that also creates some challenge in collecting good data, lest there's some industry coalition or consolidation of data, which I don't think would be happening anytime soon. Which it's not statistically significant quite yet. So I think we already touched on, if venting stops overnight, effectively your tank is, we don't have to account for those from the standing idle perspective, but effectively we have zero emissions, but that's just because the vapor space is saturating, only to be exhausted the next day when the fans turn back on.
Be able to find some relation. Okay, my vapor space purge is done every day.
Mm-hmm.
1 point.
Mm-hmm.
I leave the fans on all night, and I can get our 800 pounds.
Mm-hmm.
Why is it big disparity? I'm moving air over it.
That would be, yeah. Right. So the biggest challenge is fundamentally in the way the two equations are set up. The vapor space purge one is primarily based on the vapor pressure of whatever you had in there. So if you had RVP 10 crude oil, something big, something volatile, I should say, and you landed that tank, you emptied it out, you got it as clean as you could, there's some sludge, there's some crude, whatever's left in there, hopefully not too much. and you flip on the fan the first time, there'll be that essentially the large exhaustion of stuff, and that's going to be based on the vapor pressure of RVP10 crude oil. So that's the kicker, is that's assuming your previously stored liquid product properties. Correct. So the refinement that and you're not tied to that necessarily, but it becomes difficult to determine how or what you should then use for your subsequent vapor space purge, vapor pressure categories. Correct. Unless you've got some data collection or otherwise indicator on how to quantify that. Something to consider, though, in all honesty, the equations talk about effectively you don't count the first, I believe, half hour of because it's that vapor space purge, but first hour, half, whatever it is. But when we're at such low concentrations to begin with, or once we get to those tail days where we're at relatively low concentrations, there could be a case to say, hey, this vapor space purge isn't really representative of what's happening. I'm just running my fan. When I start up my fan, here's what's coming out. I'm measuring it. We know it's not super concentrated. Let's rely on this is more representative, and that's not, again, it's a little bit different than what's in the text, but it is not an unreasonable approach to take based on what is actually happening in the tank. Mm-hmm. Mm-hmm. Yep. Mm-hmm. Mm-hmm. So there's, and yeah, I mean, you're right in that if we have actual data and we're monitoring it, why can't we just use that? And it's, again, a function of this is the calculation tools we're given. There's not a lot of guidance. We're learning. Mm-hmm. Mm-hmm. Yeah, yeah. So we have, I think, covered the most of the cleaning stuff here. Again, the big challenge, right, is how do you address this from a PTE perspective? Do you use your worst case cleaning event in recent history? If you have no monitored cleaning events in recent history, how do you approach plugging in something to the forced ventilation calculation? You can see if your tanks group has any information you could potentially rely on previous monitoring from safety or other things, but there are certainly challenges with that, and data may be useless in the end. So it's definitely needing to evaluate based on what's in your tanks, what information you do or don't have, and developing confident assumptions to move forward. And then, of course, are emission controls necessary? Depending on your state, the answer might be yes. Depending on your permit, the answer might be yes. But even if they're not, again, odor can be a concern if you do have a dirty tank that's running for a number of days and you've got a fan blowing, you're at the fence line, and you've got a neighborhood across the street. There's some odor considerations to certainly be mindful of as well. We've been primarily focused on volatile organic compounds, the broad emission category from tanks, but we did not want to miss a hazardous air pollutant speciation as just a general topic. Right, we're talking about generally benzene, toluene, ethylbenzene, xylenes, hexane, all the 1,2,4-trimethylbenzene, all those fun ones are a speciation or subset of the total VOC emissions. Speciation details exist in AP 42, with API MPMS documents as well. Again, it's a laundry list of equations to go from your liquid weight percents to your temperature specific vapor weight calculations. What is the source of your speciation? You know, there's pros and cons for each. SDSs are ubiquitous, available, and have a number, but they're often very high, may not be useful in the accuracy we need for emission inventories or other reporting purposes. They're good for TRI, EPCA-related programs, but when we're talking crude oil, gasoline, product stream stuff, is an SDS going to have the right level of detail? I think we typically have not used SDSs for petrochemical stocks, or I guess I should say fuels-related stocks too often. Typically, we look to the industry guidance. There's reasonable data from EPCA and the EPA on speciation profiles that are generally applied to crude oil, gasoline, et cetera. Or there's always site-specific sampling as well. So having, again, good data, or at least defensible data, is important for the purposes of your hazardous air pollutant calculations. All right, we are turning the corner into the last section here on air permitting and compliance considerations. This will be a number of interesting topics relating to permitting and compliance for tanks. I will ask the question again. Any questions on the non-routine emission calculations or anything we covered thus far? No questions from the crowd here. Tony, maybe what I'll do is start rolling through these, and I can tee them up, and you can add to them as appropriate from your vantage point.
Works for me.
It's a shame that we don't have a video monitor of Tony's face up here as well. I mean, I appreciate all eyes on me, but I do need to share the spotlight. So I think we've belabored cleaning and degassing enough, but it is we've had a lot of questions from folks on it, so I just wanted to make sure we round out all the bases, right? Your requirements may vary by location. You may have controls because of state regs, like in Texas. You might have a backed determination or other permit conditions that are going to require you to control those emissions. Again, account for them in your permitting actions. Controls can be traditional add-on combustion sources. You could do a diesel flushing or some other distillate fuel to knock down the vapor pressure. Mm-hmm. Sure. That blanket. Yep. Coverage. Yep. Mm-hmm. So there's a handful of controls. Again, monitoring is the curious point to consider and work with your groups. There may be, folks that are already involved in the tank process that can hold a monitor for you and help facilitate that process without having to get a whole other person involved to take care of stuff. Tony, I'll just assume you'll jump in if you've got any comments. So I'll just keep rolling here.
The one thing on the cleaning, I don't know if you touched on a lot, was the PTE, and just getting actuals is one thing, but then if you're permitting a tank, what do you actually use to represent a worst case scenario, which brings in a whole other host of questions. So I don't want to say anything more than that, because I think we have a variety of topics to get through here in the next hour, but just wanted to throw that in there.
Sure. Again, this is a summation of a few points from the previous discussion as well, right? We want to make sure that for whatever we're doing emission calculations for, especially on the permitting and applicability side, that we have accurate vapor pressure data for. I don't think we have it in this slide, but again, I believe it was Sprague and one other New England company got substantial $100,000 plus fines and permit violations, or they didn't have permits because of bad vapor pressure coefficients. So again, we want to make sure that just like we're doing our due diligence to make sure our tank deck fitting inventories are accurate and reflective of our process, we want to make sure that our vapor pressure coefficients going into the calculations are accurate as well. Otherwise, we're going to get unuseful emission calculations coming out of it. Tank painting. So this has been kind of a curious one for a number of reasons. It can be a significant cost, and there have been clients that have, through their engineering and tank group, come back with, do we really have to paint this tank? And the answer, like any good air quality question, of course, is it depends. There may be I don't think off the top of my head there are any specific federal regulations that require tank painting at this point in time. However, there are a number of states that do require you to have your tank painted white or some other color at the state level, and that can be reason enough to justify tank painting. Or you could have it as a permit condition, again, from a backed determination or some other driver for needing to have your tank painted white. Even if you don't have a federal or state standard, a backed requirement, some other regulatory permit condition driver, should you paint your tank anyways? The mixed responses from the crowd. There's the concern of, an unpainted primer tank is not as pretty. What's that? I guess the red rust unpainted tank. Yeah. There's some optics there of is that going to be a sore spot from a community visual perspective? Perhaps not in Cushing, but in the Pacific Northwest, you may have a different matter of opinion. Granted, the other thing too, like we talked about on the emission calculation side, is if you have a white tank, you may end up with lower vapor pressures, and that may be a $1 million solution worth investing in, as opposed to a closed vent system or dealing with some NOVs in the short term. So again, a couple considerations on tank painting there. Curiously, we were working with a client dealing with a small maintenance project that had to be permitted in a state that required white tanks, and that extended to, yes, it extended to frac tanks. So, and we were not in Texas. We were well north of that. So that was an interesting one that I don't think we had historically anticipated being an issue, but kind of again working through these general topics, we've also hit on vacuum breakers, I think, pretty significantly throughout. The NSPS and KB and MacDWW requirements are that the vacuum breakers are closed unless floating roofs are being landed or filled. Typically, we see mechanically actuated vacuum breakers being the most common technology used, which they're pretty easy to fix, they're pretty easy to maintain. You can adjust them very easily as opposed to the pressure spring actuated pallet style. But these can become stuck. You can get stuck on high leg settings, even if the rest of the tank is on low legs. And you can end up with open vacuum breakers when your tank is at working bottoms. And that's going to create a deviation that you have to deal with because your vacuum breaker has opened when your tank has not been landed. Again, we're talking trivial emissions, but there is concern with, again, a deviation from a specific permit condition. Another more interesting vacuum breaker based angle is the addition of a vacuum breaker on a tank itself will only result in a handful of pounds of emissions in a given year. However, that's enough to trigger NSPS KB should you not already be subject to it. And more importantly, to better understand the full scope of project work, if your facility is wanting to add vacuum breakers to tanks because they were undersized for the current flow rate, that's one thing. But if your facility is adding vacuum breakers to tanks because they're increasing pipeline suction or fill rates and they need more venting on it, that becomes a whole nother ballgame in which you have a pretty significant permitting action to deal with, in addition to adding the vacuum breaker to your tanks as well. So there's, again, a project knowledge and being aware of what's driving changes on a tank is a critical component. Temporary tanks, we've alluded to frac tanks kind of throughout the general presentation here. There's no exemption from federal rule applicability for temporary tanks based on them being temporary in and of themselves. If you don't meet the KB compliance requirements and you're a temporary frac tank, then you're not subject to those rules. But of course, even though you're temporary, you still may have to deal with permitting evaluations and understanding what that project is and how your jurisdiction is going to handle or assess that project before you start. One interesting thing that we're seeing a lot of folks do in the biofuels world, especially if you're dealing with soy oil or other biogenic-based feedstocks, is using a nitrogen blanket or some other sort of inert gas blanket to mitigate odor issues and potentially preserve product quality. That is, like I said, typically an odor mitigation effort. From an emission calculation perspective, presence of an inert atmosphere or blanket on a tank doesn't otherwise impact the AP42 calculations. It seems like it's a little counterintuitive, but we're not talking about tanks that are explicitly closed systems, but rather have a nitrogen blanket, and there is still that exchange of vapor pressure, but rather, so there's the volatilization of material through that blanket, and we still end up with emissions. There's several several references from various AP42 guidance that indicate that even if you have an inert blanket on your tank, you don't intrinsically have a reduction or minimization of emissions. Another critical item to be mindful of from a modeling perspective is your short-term or maximum tank emission rates. Oftentimes if we're talking about a heater or a boiler or some other more straightforward piece of equipment, we can easily have an hourly emission rate that is our maximum. With tanks, it may not be as simple as dividing your total VOCs by annual emission or annual hours to get total emissions. There's TCEQ and API guidance documents that indicate how you should represent maximum emissions based on the temperatures you use, the throughput representations. It's just a few changed parameters to what goes into the equations that we already talked about. Most commonly, right, this is going to be a concern for modeling purposes, using maximum pump rates, the warmest months, et cetera, to determine those maximum hourly emission rates. So it's important to be mindful of, at the 11th hour, realizing you may or may not need maximum emission rates, and it's not just a simple division step, but rather rerunning some numbers with certain parameters to represent those maximum rates. Again, another curious situation we've observed and helped some clients kind of investigate, butane and gasoline blending. We've talked about FLIR cameras, I think, in our presentation this morning. I'm sure we've all been in some industry trade show conference, something or other, where EPA enforcement and or ad hoc inspections driven by thermal imaging cameras, or optical gas imaging cameras, I should say, occur by them driving by and taking a look at your tanks. We had an interesting instance with a client who had a question from a regulator because they were using a FLIR camera to look at some tanks, and the general course of action is to have strong records, program compliance demonstration to show that your tanks are designed to emit. They will have emissions, but did you look at our tank as we were floating the roof? Were we filling the tank or emptying the tank such that there was indeed supposed to be more emissions there? We've done our rim seal inspections. Everything looks good. We're in compliance. Your optical gas camera has not quantified emissions, but it's just shown that they're there. That is a pretty traditional, I think, approach to that situation. In this case, though, what we ended up seeing or finding out was they were looking at two tanks that were supposed to have effectively the same RVP material in them. One was manufactured RVP, so coming out of the refinery, RVP 10 gasoline. But then they were also blending different gasoline with butane to create a blended gasoline with the butane to get there. And what they were actually seeing is the blended tank apparently had a significantly higher emission rate because of that butane not apparently staying entrained in the liquid. And were they, so there's, do they have to look at either a higher vapor pressure because there's more of a higher representative RVP for that material? And, is that going to drive a permitting issue? It may be exempt in some states, but other states could require permitting depending on where you're at. So, yep, correct. Yep. It can. So speaking of high vapor pressures and materials, again, we've hit on sort of the what not to use with respect to the heavy heated vapor pressure materials. Just as a quick overview of some things to be mindful of, site-specific information is always good, if not best. Do we have a specific ASTM method that can accurately represent what the vapor pressure of our stored material is? How are we going to develop sampling frequencies? Do we have variability in the products we're receiving? Is there batching or pooling that we can, group things under? Are we using the correct test method for the material that we are attempting to determine the vapor pressure for? That has historically been a challenge for some of those other heavy materials like asphalt, or I think even the 6-oil issue was precipitated by that as well. There's not a strong or wasn't a strong or good test method to get confident or reliable vapor pressure data. So again, sampling is most certainly the best, but there's a number of considerations to know. Do you do one point in time sample for the whole year? That's a bit of a challenge. So what is your frequency? How are you representing that? Are you doing it monthly, quarterly, by batch? It's also okay to, especially when we're talking about refined products, look at things from a gasoline RVP 7 perspective, RVP 13 perspective, to use those as well, as long as that is indeed the information you're getting. There's also Antoine vapor pressure coefficients in AP 42. There's Perry's Chemical Engineering Handbook, the CRC handbook. Other data from scientific literature and sources that have vapor pressure curves. And again, just one more time, be cautious of historic literature values because we know there can be some issues with those. So be aware of the data that you're continuing to use. Meteorological data, again, just closing out this one for some of the folks that weren't here earlier. The new AP42 has updated meteorological data that's a little bit warmer than the old MET data from the existing AP42. Curiously, one of the gentlemen that was in here this morning mentioned that there may have been some communications back and forth between the API and EPA on whether or not it was appropriate for them to use that data, the new MET data. So there might be some information out there about that, but I'm unfamiliar with that specifically at this time. But for the time being, the new AP42 MET data is warmer. And if you're, again, riding that edge of vapor pressure compliance, there certainly could be a risk you need to be aware of in MET data if you're getting close to those higher temperatures and higher vapor pressure thresholds. So speaking of the EPA, to harken back to emission calculations, last November, the EPA issued a reminder about inappropriate use of AP42 emission factors, to which they specifically called out tanks 409 not being usable anymore, and then some specific tank concerns. Tank temperatures, are they really ambient, or do they receive hot stock? That's going to add potentially, again, from an emissions perspective, it's going to increase your emissions, but really we're concerned about, where does that put us from a vapor pressure TVP compliance perspective? And of course, don't rely on, defaults. How many people have had a friend who had a crude terminal permitted with RVP5 crude oil, somewhere across the country? Little did they know. So again, defaults are helpful for screening purposes, but when you're actually dealing with your assets, it's definitely not appropriate. And then I've alluded to the enforcement actions kind of on and off throughout here. Air permit violations are significant, both publicly and financially, right? NGO interest and local interest is increasing. We don't want to have deviations. We don't want to have violations, especially both for the detriment of the environment and also, again, trying to mitigate impacts or impedances to future permits or development in the area. Air permit violations, we're talking six figures quite often. The Sprague and Global Partners issues, this was that 6 oil situation, were $350,000, almost $200,000 a piece for honestly a small amount of emissions in terms of, again, we're talking about heated 6 oil tanks. So there was not, it wasn't like we were going from 1 to 1,000 tons, but we were going from fractions of tons to a couple tons, which I mean, order of magnitude is not a trivial change, but in the grand scheme, it seems kind of tiny. But because they didn't have permits and they had bad data and were operating for quite a while, apparently, that can end up with a pretty significant impact. And self-disclosures exist. They're not a panacea or silver bullet for problems, but they go a long way to preventing that from happening. If you have a robust inspection management audit program, kind of using the tools that we've been talking about, can hopefully prevent these issues from happening in the future, or catch them before they're caught on your 2-year inspection or something to that effect. Again, the EPA had another more recent document report on should the EPA conduct more oversight of synthetic minor source permitting to assure permit adherence to EPA guidance. They looked at, the gist of it is they looked at a number of natural gas extraction industries, synthetic minor source permits from Colorado and Oklahoma, and found that many of the permit limitations did not adhere to the EPA's guidance. So apparently there were a number of facilities that got permitted with synthetic minor limits that did not have the necessary monitoring, testing, compliance demonstration requirements present, or that the EPA feels is appropriate for that type of a permit. So the states got into a bit of hot water there. And ultimately, the take home for us is, especially if you have permit limits, what are they? Are you're confident and aware of what you have to comply with? How do you demonstrate compliance? Did you feel like when you got your permit, you scooted by with a free pass from your state agency, or was it a reasonably developed permit that was appropriate and has the necessary monitoring and record keeping and compliance demonstration programs built into it? And to that point, is there sufficient detail in your permits? Are you, is there a potential at-risk element you may want to consider for the next time you have a renewal coming up to beef up a little bit or something to that effect? This is always kind of, this question comes up, I think, pretty often about what to do with either a reg layer or acids or other non-hydrocarbons. It's kind of miscellaneous potpourri of stuff in tanks. So the first part, if we're talking about a reg layer or a diesel, anything where we have a heterogeneous, non-mixed situation, we're, as we talked about from a vapor pressure calculation perspective, always interested in that liquid surface interface. So if we have a discrete individual material on top of the tank, or on top of the liquid, that would be the appropriate material to use for a TVP calculation. This could be a distillate layer in a sour water tank at a refinery, produced water tank that's separated in an upstream facility. If we don't have separate heterogeneous layers and it's just a mixed tank full of stuff, then we can use an appropriately weighted average to represent that emission calculation. But if we have striated layers, we can look at what that top layer is to be our vapor pressure emission calculation representation. If we're kind of transitioning from that to acids or other non-hydrocarbon chemicals, we end up in a situation where, again, do we have good vapor pressure data? That's going to be critical. If we do, the other thing to be mindful of, especially if we're transitioning out of the organic liquid realm, is do we have something going on from a chemistry perspective where there may be, where it may be inappropriate to apply the standard calculations here to represent what's happening in the tank? Are there chemical or physical interactions that would, impact emissions modeling by way of, potential super low boiling point situations where you might be closer to flashing than actually storing a liquid material? Are there other inorganic chemical properties that would impact or potentially impede the normal volatilization ideal gas law implementation that we're talking about here? So again, just a few points and items to capture. And then finally, for this one, we've talked about the API 653 inspections in some passive detail around the drivers for the out-of-service inspections for tanks. And this is just a note on, the API standards very closely mirror the tank, the NFSS KB inspection standard timelines, but the inspection goals and inspection documentation from a KB-driven inspection versus a the difference between a KB inspection versus an API 653 inspection may not capture all of that laundry list of things we need to document for air quality compliance. So if you've been historically relying on API 653 inspection data, you may want to either make sure that your API provider knows you need a little bit of extra stuff, or you can short circuit that headache and have an environmentally focused inspection, or give them another form that has specifically what you need for NFSS KB based out of service inspections. And you've already got it halfway done. The glass is half full. Just so, make sure that, generally speaking, we have a distribution of responsibility from tank inspections oftentimes outside of the environment group to operations or somewhere else. So it just comes back to good communication between those groups. Make sure you've got strong program tools and ownership to know that whoever is doing those inspections will get the right information and do it correctly and hopefully not leave you in a tough spot. The final note on API stuff is modification reconstruction issues may arise. Again, if an API inspection indicates that, ooh, this tank is not up to whatever standard part of the code, and we need a vacuum breaker is the common example, or we need to have a couple extra roof legs because this tank was not sized or designed correctly. Those little things can increase your emissions and potentially drive or trigger permitting actions, either as part of a small maintenance project or something bigger. Tony, that's the last compliance and permitting topic. Anything substantially worth noting from your end on any of those?
I think you covered it well. Yeah.
All right, so we have a little bit of time left, and we've got one formal section here, the Barr tank emission calculation spreadsheet, or what we call BTECS. Before we jump into this, maybe for those folks that have been here the whole time or just joined us, do you have any questions on anything that we've covered thus far? And then once we get to this tank calculation stuff, this will be kind of our last hurrah before we're wrapped up here. Excellent. No immediate questions from the audience. So I think we're on track to being on or ahead of schedule. As I say that out loud now, we'll see how well I can deliver. BTECS is our a little bit of a pun play on words for the Barr tank emission calculation spreadsheet, often used to calculate BTECS-based emissions. We developed it as an Excel-based tool to estimate emissions from tanks. It is, when tanks 409 was going to be, depreciated and no longer useful, we kind of self-identified the need to have something for ourselves that turned into a larger, more broadly available tool that we have, worked with clients on and provided for industry users that they can access it for free. Additionally, in addition to running the calculations based on the new methodology, it also has the option to toggle between the old calculation method, so you can do some calculation comparison purposes as we're still kind of at the tail end of the transition period from the old to the new calculation methodology. So it does all the emission calculation stuff that we talked about today, from the routine emissions to the non-routine emissions for fixed and floating roof tanks. You can, as long as you've got chemical data and it's appropriate to use, you can enter in any type of VOC material or emissions. It can be customized. The reason why we went with Excel versus a formal spreadsheet or a formal software program is so oftentimes calculation tools like this are built into other compliance tools. So instead of having to transfer data from one application to another, by having much of the working elements built into a spreadsheet, it's very easy to add on your additional control or your additional compliance demonstration tables or other things to address your tank calculations in one spot. So I'll pull it up here in a second, but this just kind of steps through kind of some of the stuff. Even though it's in spreadsheet format, we've developed user forms very similar to how Tanks 409 used to look, except it's, we think, hopefully a bit more appropriately laid out to kind of work through your tank information. And you can enter that in. So you're not entering things in a mile-long spreadsheet row, but rather you get a human readable, user interface that you can easily enter in information for tank properties, for floating roof properties. Again, historically, when we've made spreadsheets in the past or other tools we've seen, it's, one column for the 1,700 different deck fittings. Again, a little more user-friendly format to help get the data entry process accurately done and easy to look at or reference as well, again, as part of that compliance program or deck fitting inventory. And again, so what it does do, though, we've got the user forms that give us the quick reference or quick ability to enter information, to see information, and then it just keeps it in a tabularized format. Chemical property information, too, is laid out in a similar way. where we have essentially the library of chemical materials from AP42, plus you can add things in, you can speciate out components, you can specify whether you're using RVP, a second order polynomial for vapor pressure curves, Clausius-Clapeyron, vapor pressure coefficients, Antoine coefficients, or if you have a vapor pressure curve, you can specify what that data is and fit a curve to it within the program itself. And then enter your other physical properties, add some notes, and again, have a more human interfaceable way to interact with your vapor pressure data. And again, once you enter it in, it puts it into a tabular format for use in the calculations. Meteorological data, you can enter in site-specific information if you got it. Otherwise, you can reference metadata from the AP42 database. And if you have a mixed bag or you're trying to figure out using partial data, you can ultimately see what information gets pushed into the calculations here to make sure that you end up with the right information. And then monthly storage tank information. So for each tank you put in, you end up with 12 months of potential data entry. You specify the product, you specify the throughput, you can specify a bulk liquid temperature if you have to, and then that goes into the calculations. For landing events, whether it's refilling or landing a roof or refilling a roof, we've got a user form again that walks through the process of what was going on with the tank, what happened. Did you have a liquid flush? When did you refill it or did you not refill it? And that goes through and again puts those parameters into the calculation. Similar to correct. Yep. Yeah. Similar for the tank cleaning stuff, we've got, again, a developed form that just you walk through the process. When did your event start? A couple preliminary previously stored product information. And we've got up to 50 days where you can indicate, did you have a vapor space purge, yes or no? What was the heel configuration? What was your ventilation rate, hours per day, concentration, and a couple different parameters to develop the different methods. Yeah. Oh, per event. You can do multiple events up to 50 days. Or should you have something that stretches on, you can essentially daisy chain one event to continue for the next one. So what about reports? So, we've kind of gone through all this nice, useful data entry stuff. Again, we talked about a lot, how do we verify or validate the emission calculations that we're doing? We have one thing that Tanks 409 did good, and that might just be a result of it being the only thing for a long time, is it had pretty good human readable printout tables that when you printed a report out of Tanks 409, you could see here are the tank properties, here are the meteorological data, here's the speciation stuff, here are the intermediate calculations that go into calculating our emissions. We've developed report tables that are pretty similar to the Tanks 409 output, so that for submittal as part of a regulatory package, you have a clean, easy to follow along table of tank calculations versus a spreadsheet that has a lot of, again, buried equations and somewhat difficult to audit or understand things. And we include intermediate calculations for both the routine and non-routine emissions. So we have detailed tables for all of the emission calculations. So that being said,
Is that spreadsheet that we set it up per tank for month?
yeah.
All your tanks are in one tank?
Yep, so there's a little latitude in if a user wants to have it represent one single facility or multiple facilities. You're kind of constrained by the metadata location, but generally speaking, the way we see it best set up is one spreadsheet per facility or per location. So you can have one tank or 100 tanks in there, whereas some state agencies have attempted to create their own calculation tools that are very cumbersome and limited to one spreadsheet per tank, which is, hey, at least you're not in Minnesota, Gary. There you go. That's a.
And the calculation should be spread. They mean by Visual Basic, have you push a button or the actual?
Combination of both. So we have a number of user-defined functions to facilitate the adding and removing of tanks and making sure that we don't have issues with equations getting bumped or broken by people. And granted, the spreadsheet is also locked down, but that's why we have the printable reports that pull out the data and show the intermediate calculation steps along the way. So even though we have a user-defined function that correlates with an equation in AP42, you can see here is the value for this, vapor density calculation. That's one factor of one part of one equation that gets us to our total emissions. Ooh, we may have a challenge here. We have the capability. So unfortunately, the computer here, the technical capabilities of the Excel version will not run. I could and I will, but with Tony on the call and the recording thing happening, I am, what's that? Okay. Oh, well, Tony had dropped. In that case, maybe what I can do is I want to shut down. I'll shut down the Teams call here, and for those that are curious to check out the spreadsheet quick, I can do a quick demo and call it good. So in closing, covered all the good stuff. And our key takeaways, I've belabored these points all day. Pay attention to the details. Pay attention to when you're changing stuff on your tank. Pay attention to your calculations. Incorporate cleaning and degassing stuff into your emission inventories and permitting. Understand what your regulatory burden is, what your permits say. Make sure you've got the folks that are responsible for compliance on top of that stuff. And then be aware of stuff that changes, whether it's a regulatory basis or local issues, or even facility operational changes that could impact your vapor pressure or emissions. For those that were able to grab a flash drive, we just have a couple links and references to some of the documents that we've been talking about. If you're curious about the spreadsheet after I show it, if you go to barr.com/BTECS, that'll get you there. Again, some links to some of the other documents and useful tools that we've talked about. And there we go. So I will set up this computer really quick to just show the spreadsheet. While I'm doing that, any questions or comments or other notes or items?
So you had butane blowing through gasoline in your example. So that didn't raise the problem. What's the best way to quantify all those things? You have to know how much butane is going through and then what your vapor pressure product is going at.
So that is a good question. I am but a messenger in this case. However, the way I understand what they ended up doing was some, on the way of my hands, engineering math to quantify beyond just a ratio blending, but actually looking at constituent-wise how much they're putting in and doing some math around how that.
How much did stay?
Correct. Yep. Okay. So that has also been an issue with.
Vapor pressure still has to be below So if they were blending gasoline, they're probably blending into the RVP limit for the area.
Mhm. Yep.
So they didn't really, so they had to worry about quantifying butane emissions more than they had to worry about increasing emissions on the gas.
I believe so, yes. Yep.